Hello, and welcome to The Sleepy Scientist. I am glad you are here tonight, ready to slow down and let your mind drift. In this gentle journey, we are heading toward the smallest planet, the swift and silent world nearest the Sun, Mercury. Before we begin, I would love to know where in the world are you watching from and what time is it there? If you enjoy these calm explorations, a like and a subscribe go a long way in keeping this channel moving. And to those who have already subscribed, thank you for being part of this quiet orbit together. If you would kindly press the notifications bell, you will never miss the next voyage into the cosmos. I can only hope this video is not so interesting that it keeps you awake, though if it does, at least you will wake tomorrow with a few more facts quietly woven into your dreams. So here is the thought to carry you forward. How can a planet scorched by the sun also hide patches of eternal ice? Mercury is a world of paradoxes. It is the smallest of the planets, yet it holds one of the largest metallic cores. It circles the sun in just 88 days, yet its day, sunrise to sunrise, lasts for nearly half a year on Earth. It is a planet that knows only extremes: boiling heat in the light, freezing cold in the dark, and silence everywhere because there is no air to stir. Despite being one of Earth's closest neighbours, it remains one of the least understood worlds in the solar system, a tiny companion often overlooked as we gaze outward toward giants and rings and moons. But Mercury has its own story to tell, carved in stone and shadow, written in scars and whispered through the peculiar rhythm of its orbit. This journey will not rush. Instead, it will unfold in patient steps, as though walking beside the planet on its slow rotation. We will look at how ancient civilizations made sense of Mercury's fleeting appearances in the twilight sky, why it was named after messengers and scribes, and how its orbit challenged astronomers for centuries until relativity offered an answer. We will explore its battered face, the scars of collisions that date back to the dawn of the solar system, and the giant Caloris Basin, a wound so large that it reshaped half a hemisphere. We will climb the Great Scarps, cliffs created when Mercury shrank as its core cooled, and we will linger in the polar shadows where radar has revealed bright signatures of ice, paradoxical against the nearby sunlight. From there we will step inward, imagining the enormous iron heart that makes Mercury unlike any other planet, and we will see how that heart still stirs enough to generate a faint magnetic field, something no one expected from such a small body. We will also follow humanity's visits to this elusive neighbour, the fleeting glimpses of Mariner 10, the rich maps from Messenger, and the promise of new discoveries from Bepi Colombo, now on its long spiral toward orbit. Each chapter will carry us closer to understanding why Mercury, though silent, is a key to reading the solar system's past. As you listen, let the details come slowly, like stars appearing one by one in the night. Mercury is not a planet of spectacle, but of subtlety, a world that rewards patience with clarity. By the end of this journey, the swift point of light you may have glimpsed at dawn or dusk will feel less like a stranger and more like a familiar companion, a reminder that even the smallest planet has a profound story. And perhaps the quietest question to begin with is this: what can a world of such silence and extremes teach us about the balance of worlds, and even about ourselves? At the very edge of dawn, just before birds decide it is morning, a modest spark lifts itself out of the brightening haze. It hovers for a short while and then retreats into daylight. In the evening it performs the inverse, glinting briefly in the afterglow and sinking towards the horizon, as if it is somewhere more urgent to be. That quicksilver routine made this planet the most elusive of the visible wanderers. From that elusiveness grew a garden of names, a thicket of myths, and a handful of scientific riddles that nudged human curiosity forward by small, steady steps. To the Romans, the fast-moving point was Mercury, the messenger with winged sandals, patron of merchants, travellers, and clever talk. The choice feels almost inevitable once you have watched the planet for a season. It never lingers high in the sky like Jupiter, nor swells with dramatic phases like Venus. Instead, it darts between morning and evening, delivering its brief glimmers on a schedule only the careful can anticipate. Hermes in Greece carried a similar portfolio, the crosser of boundaries, the guide, the quick thinker. A planet that refuses to dwell in one half of the day, that appears in liminal light, seems made for a god of thresholds. Earlier still, in Mesopotamia, scribes tracked the wanderers on clay and named this one for Nabu, keeper of wisdom and writing. The association is more than poetic. Predicting Mercury demands records. It requires noting when it first peaks from the dusk, how far from the sun it appears at greatest elongation, and when it will trade evening for morning again. A good table of dates is as much a talisman here as any incantation, and so a god of script and tally suits the planet's temperament. In Egypt, the link was with Thoth, the ibis-headed deity of timekeeping, calculation and letters, another reminder that to understand Mercury is to count carefully. In India, the planet is Buddha, quick-minded and auspicious, whose name threads through languages into the weekday many of us call Wednesday, Mittwoch, Mercredi, Miércoles, Mercoledi, a quiet calendar-wide tribute to the little runner near the sun. In China it is the water star, a name drawn from the 5 elements of classical thought. Water might sound odd for a sun-baked world, but in that philosophical system water is the element of intelligence, depth and shifting form, all good metaphors for a light that refuses to stay put. Why messengers, writers and wise counsellors? Partly because the planet keeps appointments with the horizon. It arrives early, leaves early, and rarely grants more than a modest audience. Partly because it moves with a speed you can feel even without a telescope. Night after night it changes position faster than any other planet except Venus. And it changes allegiance too, now attending the sun at dawn, now escorting it at dusk. A messenger crosses spaces others hesitate to cross. Mercury does that in the sky with habitual grace, and to follow it well, you must write, compute, and remember. If you are an early sky watcher, Mercury's most confusing habit would have been this double life. Many cultures at first assumed there were 2 different stars, one that appeared before sunrise and one that shone after sunset. The Greeks called the morning apparition Apollo and the evening Hermes. Similar dual naming happened elsewhere, with dawn and dusk personalities treated as siblings or rivals. Only patient observation revealed the trick. The planet never strays far from the sun because it orbits inside Earth's path. It can only be seen in the twilight windows, and as it rounds the sun from our perspective, it alternates which side of day it inhabits. 1 world, 2 roles. Even after the unity was understood, other puzzles remained. Mercury never climbs high above the horizon unless the geometry is kind. In spring evenings, for northern observers, the ecliptic, the path of the sun and planets, stands steeply to the western horizon, and Mercury gets a little extra lift. In autumn mornings, the same happens in the east. Conversely, in the wrong seasons, its best show is meagre. Add the fact that the planet is small and the atmospheric turbulence near the horizon is strong, and you see why Mercury has always felt like a secret reserved for those who make the effort. Telescopes sharpen that secret, but only so far. Through magnification, Mercury displays phases like a tiny Venus, thin crescent, half gibbous, proof that it circles the sun inside Earth's orbit. Yet surface detail stays shy because we usually view it through a thick, unsteady slice of air. Early astronomers tried to map dusky patches across its disk. The maps disagreed like stories told from memory of a fleeting meeting. In the 19th century, some observers thought Mercury turned only once per year, always showing the same face to the sun. It seemed plausible since tidal locking is common. The idea lived in textbooks for decades, a settled fact born of difficult data, until radar measurements in the 1960s revealed a subtler truth. Mercury rotates 3 times for every 2 orbits. The planet's day is not endless after all. It is simply very long and unusually choreographed. A messenger, yes, but one who keeps a peculiar rhythm. Another riddle was written not on the disk, but in the path. Careful tracking revealed that Mercury's elliptical orbit slowly swivels in space. Most of that precession is expected. The gravity of other planets tugs at Mercury and advances the point of closest approach, the perihelion. But there remained a small leftover, a few dozen arc-seconds per century that Newton's equations could not quite capture. For a time, astronomers proposed a hidden planet closer to the Sun, named Vulcan, whose pull might explain the extra drift. Searches in the glare yielded rumours and hopes, but no reliable body. The leftover persisted like a loose thread in an otherwise impeccable garment. In 1915, Einstein's general relativity tied the thread. Near the Sun, space-time's curvature deviates just enough from Newton's flat ideal to nudge Mercury's orbit forward by exactly the measured amount. The smallest planet, so hard to see, helped confirm a theory that reshaped our understanding of gravity. Though sober astronomy eventually replaced myth with mechanism, the older stories leave an imprint worth keeping. There is wisdom in linking a difficult-to-spot planet with gods of record and measurement. Mercury rewards scribes, those who write down the evenings and mornings when it first appears and last fades, who note how far it stands from the Sun and how steep the ecliptic will be when it next peaks out. There is aptness in choosing messengers too, because Mercury seems to travel between realms, day and night, seen and unseen, sacred and ordinary time. Even the Chinese name Water Star catches a truth. The planet's appearances flow. They seep into a schedule shaped by geometry rather than spectacle. And if you miss one, another comes, slightly altered, like ripples arriving at shore. The planet has a few grand performances among its modest ones. Now and then, when the angles are exact, Mercury passes directly between the Earth and the Sun and writes a tiny perfect dot upon the solar disk, a transit. It is a minimalist drama, a moving pinprick against a blinding backdrop, visible only with filters and care. The first telescopic observation of such a transit in the 17th century was a triumph of prediction and timing, a moment when numbers on paper turned into a physical shadow crawling across the star that rules our days. If you have ever watched one, you know the particular feeling. You're seeing not a light, but the absence of light. And from that absence you reconstruct an entire world. No chapter about Mercury's myths would be complete without mentioning the idea, popular in astrology, that Mercury sometimes goes retrograde and upends plans, muddles messages, and tangles travel. The astronomy behind the word is simple and harmless. Because Earth and Mercury move at different speeds on nested tracks, the faster inner planet occasionally appears, from our moving vantage, to slow down, halt and drift backward against the background stars for a few weeks. It is an optical effect of relative motion, common to all planets at times. Your train pulls past a slower one, and, looking sideways, the other train seems to slide backward, though both go forward. The sky has its own version of that platform illusion. Whatever mislaid keys or missed connections we suffer owe more to human habits than to a small airless world minding its orbit. For ancient observers without telescopes, all of this complexity condensed into a practical art. You learned where to look. You memorized that, in a good season, Mercury will appear not long after sunset to the west, or not long before sunrise to the east, seldom far from the sun's path. You took note of its change from a mere glitter to a small, steady point as the sky darkened, and of how quickly it surrendered to brightness. You taught apprentices to watch with the corners of their eyes, where faint light is easier to catch, and to glance back only when the spark had announced itself. You understood that the planet's predictability lives under a veil of brevity, and that most people will never have seen it, though it is one of Earth's nearest neighbours. And so the old names linger, not as scientific categories but as invitations to look more carefully. Mercury as Hermes, crossing borders, as Nabu and Thoth, writing the tally of appearances, as Buddha, quick and clever, as the water star flowing in time. These are metaphors, yes, yet they're also accurate in a way that numbers sometimes fail to feel. The numbers can tell you that Mercury's greatest elongation stretches to only a few tens of degrees from the Sun, that its cycle from evening to morning averages roughly 116 days, that its orbital period is 88 days. The names tell you that this is a planet of thresholds and briefness, of notes taken at the edge of light. If you step outside on the right evening and find a clean western horizon, you can join a lineage older than history. Wait for the sky to become a deep cobalt. Watch the bright star of Venus if it's there. Let your eyes rest a little below and to one side of the place where the sun set. When a small, stubborn spark declares itself, you will have found not just a planet, but a story. For a few minutes, your world contains a messenger slipping away to deliver its next appointment, and though you may not carve the sight on clay or attribute it to a god, you will feel the same modest satisfaction that those earlier watchers knew, a private handshake with the sky recorded not in tablets but in memory, and renewed if you wish at the next dawn. Mercury moves like a thought. While Earth takes a full 365 days to circle the Sun, Mercury completes the same journey in only 88 days. A tight, fast loop close to the furnace. Speed is not a luxury here. It is a requirement. The nearer a planet orbits the Sun, the deeper it sits in the Sun's gravitational well, and the faster it must run to avoid falling in. Mercury obliges by racing along at tens of kilometers per second, with its pace quickening as it dives toward closest approach and easing as it swings away. The orbit is not a perfect circle but an ellipse, noticeably stretched, so the planet's distance and speed breathe in and out with every circuit. The result is a year that flies past, and a sky show that would perplex anyone expecting Earth's tidy day-night rhythm. Orbit is only half the choreography. Spin writes the other half. For a long time it seemed reasonable to assume Mercury was tidally locked, always turning the same face to the Sun, the way our moon forever shows us one side. That would have simplified matters, one hemisphere in endless day, the other in endless night. Reality is more interesting. Radar experiments in the 1960s revealed that Mercury rotates exactly 3 times on its axis for every 2 orbits around the Sun. This is the 3:2 spin-orbit resonance, a neat little ratio that balances tidal forces and internal friction on a path that is not circular. The Sun's pull tries to tug the planet into a 1-to-1 lock, but the eccentric orbit complicates the talks. Over deep time, the system found a compromise that wastes the least energy. 3 turns for 2 laps. The consequences for time on the ground are quietly astonishing. The length of a solar day, the interval from one noon to the next as the Sun crosses the sky, is not the same as the length of a sidereal day, one full rotation relative to the distant stars. On Mercury, the solar day lasts 176 Earth days. Yes, the planet with the shortest year has a day that stretches longer than 2 of its years combined. If you planted a sundial on a basalt plain and promised to stay until its shadow pointed straight north again, you would be there for months. Because the orbit is eccentric, the Sun's apparent behaviour in the sky is unlike anything on Earth. As Mercury glides toward its closest approach to the Sun, it speeds up along its track. In certain longitude bands for a short time, that faster orbital motion can outpace the steady rotation of the surface beneath it. The effect for an observer is surreal. The Sun nears the meridian, slows, stops, drifts slightly backward, pauses again, and then resumes forward motion. Noon hesitates. Sunrise might stall on the horizon, as if the sky needed to take a breath before committing to day. Later, near sunset, the same peculiar hesitation can play out again. There are two broad regions on Mercury where this dance is most pronounced, roughly opposite each other, chosen by geometry as the places where the resonance and the varying orbital speed conspire most dramatically. Now imagine your senses in such a place. There is no air to tint the sky blue, so even at noon the heavens are black, salted with stars. The sun's larger than we are used to, swollen by proximity. Dawn drags on for many Earth days as light crawls across crater rims and pours down their inner walls. Shadows inch back with a patience that invites comparison to glaciers. Rocks in sunlight soak up radiation without mercy, while rocks, still in night, surrender their stored heat straight to space. Without wind to shuttle energy around, the boundary between hot and cold is a line drawn by topography and the pace of the sun's crawl. You could walk across a boulder's Jahor and feel the world switch between oven and icehouse with a single step. The 3-to-2 resonance also lays a faint fingerprint on geography over geologic time. The same longitudes face the sun at or near closest approach every other Mercurian year, receiving the most intense doses of sunlight on a repeating schedule. It is reasonable to suspect that such repeated extreme heating and cooling, cycle after long cycle, might subtly change surface materials in those belts, compared with regions that spend their noons when the planet is farther from the sun. Spacecraft have indeed mapped variations in reflectivity and composition across the planes. Impacts and ancient volcanism account for much of the patchwork, but the relentless rhythmical roasting and cooling tied to the resonance likely contributes a quiet, cumulative seasoning to the crust. If you're fond of thought experiments, you can sketch out life's logistics under such a sky. A settlement could, in principle, surf the Terminator, on the line dividing night from day, to stay within the mildest possible band of temperature. The Terminator creeps very slowly on Mercury, so a habitat might trundle along the ground at a walking pace for weeks, always keeping dawn just ahead or dusk just behind. It sounds romantic until you plot the terrain. The line wanders across crater rims, down into basins, over ridges, through rubble. The planet offers no roads, only geometry. In practice, a more practical strategy would be to carve into crater walls at high latitudes, where the sun skims low and shade can be engineered. The resonance sets the schedule either way. Long days, longer patience. For all its immediate sensory oddities, Mercury's orbit also hides a famous quantitative riddle that nudged physics forward. Since the 19th century, astronomers knew that Mercury's elliptical path precesses. The ellipse slowly swivels in the plane of the orbit, so that the point of closest approach to the Sun and the perihelion advances over time. Most of this precession comes from gravitational tugs by the other planets and from small effects like the Sun's slight oblateness. When you add up all the Newtonian contributions with care, though, a residue remains, about 43 arcseconds per century of extra advance. That is a very small angle, but it was measured, checked, and stubborn. For decades, the mismatch tempted explanations that now read like charming detours. Perhaps there was another planet even closer to the Sun, christened Vulcan, whose unseen gravity supplied the missing nudge. Observers reported spots near the solar limb during eclipses and in routine watching, but no candidate survived scrutiny. Dust rings, solar bulges, altered laws, proposals flowered and fell away. The sky appeared to be whispering that Newton's framework, immaculate in so many domains, needed an addendum for places where gravity is intense. In 1915, the addendum arrived as a replacement. Einstein's general theory of relativity recast gravity as the curvature of spacetime caused by mass and energy. Planets follow the straightest possible paths in that curved geometry, which, to Newton's eyes, look like orbits subject to subtle extra forces. When the new equations were applied to Mercury's situation, deep in the Sun's grip where curvature is non-negligible, they produced the exact missing 43 arcseconds per century. It was a triumphant moment, not because an anomaly was patched, but because a deeper idea made a stubborn fact inevitable. Mercury, the fleet messenger of myth, delivered a message about the shape of reality. Relativity's correction is not an everyday concern for a hypothetical Mercurian farmer watching dawn tiptoe across a field of stones, but it is baked into the tables that navigators, mission planners, and radio scientists use. When a spacecraft aims to slip into orbit, its trajectory is computed with those corrections already in place, so that math and world coincide to the meter. In that sense, Mercury is both an object in the sky and an instrument on the lab bench, proving every day, very slowly but very surely, that space-time near a star is a little curved. All this might sound elaborate for a small world, but there is an elegant theme running through it. Extremes tuned into harmony. The extreme speed near the Sun is balanced by the extreme patience of a day. The extreme eccentricity of the orbit settles into the exactitude of a 3-2 rhythm. The extreme closeness to the Sun reveals the extreme subtlety of gravitational geometry. If you listen for a minute, the planet seems to keep a metronome you can count. 3 spins, 2 orbits, 1 long noon. A hesitation in the sky where motion cancels motion. A processing ellipse that advances by a sliver measured across a century. It is swift, but it is not hurried. So picture yourself under that large sun in a landscape of crisp shadows. You watch the star drift, stall and drift again. You feel, even without wind, that the world is moving fast and living slowly. Somewhere, far overhead, equations describe the path exactly. Somewhere back on Earth, a clock and a radio track the planet's heartbeat as it rounds the perihelion and slides toward aphelion, year after abbreviated year. And here at your feet a pebble warms, another remains cold, and the line between them advances by millimeters in an hour, perfectly on time with the smallest planet's great deliberate clock. From afar, Mercury looks like a cousin to the Moon, a grey sphere stippled with craters, ringed basins, and faint rays that trace the aftermath of ancient blows. Both worlds are airless and old, both lack the softening touch of weather, and both wear their history openly where light and shadow can read it. Yet the resemblance is only the first impression. Spend a little time with Mercury's face and the differences begin to speak. The craters are cut into a denser, more metal-rich world. The plains are broader in places and in many regions smoother than lunar fields. And the textures tell a story that alternates between relentless bombardment and episodes of quiet flooding by lava long since stilled. On an airless body, the default sculptor is impact. Meteoroids and asteroids arrive at hypervelocity, turn motion into heat and pressure in an instant, and reshuffle the crust like a chef flipping a hot pan. The anatomy of the result depends on size. Small impacts carve simple bowls with sharp rims and blankets of ejected debris thrown around them like frozen splash. Larger impacts rebound to the crust to raise central peaks, and larger still create peak ring basins where a circle of mountains lifts from a floor that briefly behaved like a stiff fluid. Mercury has every entry in this catalogue, from tiny pits you could cover with a city to the continent-scale Calorus Basin that dominates a hemisphere. Because there is no rain to round edges, no rivers to carry rubble away, and no plants to anchor loose grains, the record remains legible. Age is written in sharpness, crisp rims are young, Softened rims, cut by later strikes and spattered by secondary craters, are old. Between and beneath the scars lies the quieter part of the story: plains. To the eye, Mercury's surface resolves into two broad textures that repeat across the globe. One is the intercrater plains, a patchwork of ancient ground crowded with overlapping small craters. Stand on such a plain and the horizon is a low, pocked undulation, as if you were walking across hammered metal. These regions are among the oldest surviving surfaces, likely assembled early in the planet's history, when impacts were so frequent that ejecta and melt overlapped into a rough, unified fabric. In places, the intercrater plains look almost saturated with dents, each new crater erasing and rewriting the last. The other texture is smoother, the aptly named smooth plains. These are broad sheets that fill low areas and mantle older terrain with a surface that, under lotion or sun, gleams like poured stone. For years, scientists debated their origin. Were they mostly impact melt pooled from the giant basins, or were they volcanic, true lavas that welled up through fractures and spread out in floods? Close mapping tipped the scales toward volcanism in many regions. Flow fronts, subtle levees, and chemical signatures all point to eruptions that once poured across Mercury's lowlands. In some basins, including the interior of Caloris, smooth plains have a different colour and composition from the surrounding ground, suggesting material drawn from depth rather than merely remixed crust. The picture that emerges is of a restless early world, battered by impacts, yes, but also warm enough to bleed rock onto its face and pave over older scars. If you skim across Mercury from orbit, the boundary between these textures sometimes appears abrupt, sometimes gradational, as if lava used the impact-broken ground as a guide, ponding in lows and edging up against older highs. Wrinkle ridges crisscross portions of the smooth plains, low sinuous folds that rise like frozen waves. They hint at broad, gentle compression after the lava cooled, a surface echo of the planet's global tendency to shrink as its interior chilled. Where ridges intersect crater rims, you can watch geometry negotiate with geology. Straight lines of collapsed circles meet curved, wandering swells, and the compromise is drawn in shadow. Craters themselves come in families that help decode time. Fresh, bright-rayed craters stand out like new chalk marks. Their rays can run for hundreds of kilometres, dusting the ground in streaks that thin with distance. Farther from the fresh crater, small secondaries pelt the surface in graceful chains, each formed by chunks of debris launched on ballistic arcs. With age, rays darken, and the sharpness fades as tiny micrometeorites garden the topmost grains, and as later strikes pock the pattern. On Mercury, space weathering works in tandem with chemistry. The solar wind and intermittent micrometeoroid rain can strip volatile elements, redden surfaces, and alter reflectivity. Subtle colour variations, invisible to the naked eye but clear in calibrated images, map out patches with different histories and compositions, adding nuance to the simple old-young ordering that sharpness provides. If you step mentally onto the intercrater plains, you feel the antiquity. The ground seems to have accepted a long, gentle hailstorm, and then healed only by accumulating more of the same. The craters overlap until circles become polygons, and the eye starts to group them into terraces and low swales. In contrast, smooth plains feel younger, less resigned. They flow around islands of older terrain, lap at crater rims, and in some places bury them entirely so that only ghost rims peek through as low rings. Where a smooth plain enters a basin through a breach, you can almost see the direction the lava took, guided by gravity and relief the way water would be on Earth, though the flow here was molten rock moving slowly under a black sky. Mercury's likeness to the Moon is strongest in the palette and in the prevalence of craters, but the differences matter. Mercury's gravity is higher, and its crust and mantle composition differ, so the thresholds for central peaks and peak rings shift. Many of the smooth plains are more extensive than Luna Maria of comparable basins, hinting at a planet that, despite being small, had a surprisingly robust volcanic phase. Everywhere you look, lobate scarps, those planet-spanning cliffs that mark global contraction, cut the story with a separate, quieter script. On the Moon, such scarps exist but are fewer and smaller. On Mercury, they are a signature. A scarp will slice across a smooth plain, lifting one side like the edge of a rug. Elsewhere it will run through an old crater, offsetting the rim and making a circle into a chord. Each crosscut writes a line in a timeline. First the impact, then the lava, then the shrinkage, or perhaps a different order where the relationships reverse. Some of Mercury's most intriguing bright patches dot crater floors and rims where smooth plains and rougher ground meet. These are not simply sunlit slopes. They are deposits with distinct reflectance and colour, often clustered around shallow, rimless depressions known as hollows. While the hollows themselves are a topic of their own, the context matters here. They punctuate both textures, reminding us that the surface is not merely a static mosaic. Chemistry changes under the extreme light and cold, and the skin of the planet remains reactive enough to sculpt these small, fresh-looking features atop a very old canvas. Because there is no atmosphere to carry fine dust far afield, texture and tone stay local. An impact with a certain energy and angle throws a characteristic apron of blocks, shards, and dust. Where that apron drapes an intercrater plane, it adds roughness to roughness, raising the grain of the surface. Where it lands on a smooth plane, it pebbles the sheen and draws the eye to subtle boundaries that become most obvious at low sun. This is why photographs taken under different lighting tell different truths. High sun shows composition, low sun shows relief. A bleak sun void reveals the stitching between terrains that might otherwise look uniform. The longer you look, the more the face resolves into narrative. Here is a smooth plain that must have flowed in after a basin formed, because it buries half the rim and leaves buttes of older rock protruding like islands. There is a field of intercrater terrain so pitted it suggests ages when the impact rate was ferocious, perhaps in the tail of the era that built the Great Basins. Beyond that, a ray system overlays both textures, declaring itself younger than everything it crosses. A scarp kinks the rays, so the faulting postdates the strike. In a single image you can stack events like layers in a cake and taste in order, bombardment, volcanism and contraction. If you compare this to Earth, the differences feel almost radical. On Earth, plate tectonics and weather arrays, oceans swallow basins, mountains rise and wear down, and life fills the gaps with soil and forest. On Mercury, memory is the default. The planet's face is an archive where the filing system is angle of light and the index is crater density. The two dominant textures, intercrater plains and smooth plains, are like two voices in a duet. One is ancient and rough, a murmured accompaniment that runs almost everywhere if you drop the melody out. The other is younger and lyrical, flowing into the rests and tying phrases together. There is a quiet beauty in the way these textures meet. Along some boundaries, smooth lava tips over the rim of a crater like a slow waterfall, freezing into a rounded ledge. In others, it embays an older hill and leaves a slim moat around it, an accidental map of older topography preserved as a negative. On intercrater plains, small new craters can make their own miniature smooth patches when their melt pools and cools as glassy sheets. Scales echo the tiny copies the large. For a listener drifting towards sleep, perhaps the most calming thought is that Mercury's surface is honest. What you see really is what you get. There are no clouds to stage a show. There are no forests to conceal a ridge. There are no waves to continually redraw a shore. Craters, plains, and the lines between them stand where physics put them, awaiting the slow change of micrometeorites and the gentle settling of dust. The resemblance to the moon invites familiarity. The differences invite curiosity. And in the patient alternation of rough inter-crater tapestries and smooth volcanic sheets, you can hear a rhythm, strike and stillness, chaos and calm, a small world's face composed of scars and the quiet stone that grew between them. If Mercury's face is a library of scars, the Caloris Basin is its great illuminated manuscript, a page so large that it changes how you read the book. Seen from orbit, it is a tremendous oval framed by mountains, its interior paved in places by smoother, lighter plains, its edges frilled with ridges and broken ground that spread outward like the skirts of a stone-made splash. Caloris is among the largest impact basins in the solar system, measuring about 1,550 kilometers across, wide enough that if you set it down on Europe, mountain ring to mountain ring, it would span countries. It was born in a blink and has been explaining itself ever since. Imagine the moment of impact. A body tens of kilometers wide arrives at hypervelocity, striking with an energy that turns rock into liquid and vapor for a heartbeat. A hole is excavated, not like a shovel digs, but like a shockwave scours, instantly and all at once. The crust rebounds, collapses and rebounds again. Concentric rings form as different layers of the crust respond like nested springs. Debris sails out on ballistic arcs and falls in thick blankets. Some of it slides and flows while still hot, spreading into lineated aprons beyond the rim. Then the violence stops, and Mercury holds still long enough for the heat to leak away into space. What remains is not merely a crater, but a multi-ring basin, a kind of planetary bullseye, and for Mercury, Caloris is the exemplar. The ring itself rises in a series of mountain belts called the Caloris Montes, not a single wall, but a chain of rugged, discontinuous heights. Between ring and ring, terraces and ridges record the settling of the crust as it negotiated a new equilibrium. Outside the rim, the ground is rumpled into ridges and grooves that stretch for hundreds of kilometers, aligned with the basin like ripples around a dropped stone. This lineated terrain is ejecta and disturbed crust dragged and folded by the force of the blast. The pattern repeats the physics. Materials near the surface were ejected and redeposited radially, while deeper layers slumped and slid, creating textures that geologists can read like a seismogram. Inside Caloris, time added new chapters. Much of the floor is mantled by smooth plains whose tone and chemistry differ from the surrounding highlands. For years, scientists debated whether these plains were largely pools of impact melt or later volcanic floods. Close inspection by spacecraft found signs that many of the smooth interior plains are volcanic, subtle flow fronts, embayments against older hills, and compositions that point to material erupted from depth rather than simply melted and refrozen where it lay. In other words, the basin did not just freeze, it invited lava. The Great Wound became a lowland where magma could reach the surface more easily, and so Caloris grew a calmer skin after its fiery birth. One of the most eye-catching features within the basin is a web of troughs called Pantheon Fossae. From above it looks like a stone spider's web or the spokes of a wheel, with narrow graben, extensional fractures where the surface has stretched and dropped slightly, radiating from a central area. Near that centre sits a curious bright-rimmed depression known as Apollodorus, which some interpret as a volcanic vent and others as an impact scar that later interacted with tectonic processes. The geometry tells a tale of stress. As the plains cooled and perhaps as the basin floor adjusted to loads and the planet continued its global contraction, the crust cracked in patterns that radiated and intersected, leaving this lace of troughs as a memory of strain made visible. Caloris is old, probably forged during the late heavy bombardment roughly 3,900,000,000 years ago, when the inner solar system was clearing its throat of leftover planet-building debris. That age makes its preservation on Mercury especially valuable. On Earth, a structure like Caloris would have been erased by plate tectonics, blanketed by sediments or gnawed by weather. On Mercury, it has sat in the black sunlight modified, yes, but still legible. Its combination of impact structures, volcanic resurfacing, and later tectonic overprints offers a compact syllabus in planetary processes, how to make a gigantic hole, how a crust cools and contracts, how magma takes advantage of fractures, and how the memory of a single moment can shape eons of aftermath. If you follow the rings with your eye, and then let your gaze drift across the globe to the point exactly opposite the basin, the antipode, you encounter one of Mercury's most beguiling landscapes, the so-called weird terrain. It is a field of jumbled hills and knuckled blocks, as if a once smooth plain had been shoved from below by invisible thumbs. The blocks sit at odd angles, the valleys between them wind and twist, and the overall effect is of organised chaos, like a chessboard melted and then refrozen mid-move. Early mappers, charmed by its strangeness, gave it the affectionate name that stuck. The leading explanation for this weirdness begins with a simple property of spheres. Shock waves from an impact do not merely spread along the surface, they also travel through the crust and mantle. On a sphere, waves launched by a great blow spread out and then reconverge at the antipode, focusing energy like sound, focusing in a whispering gallery. When the Caloris impact shook Mercury, deep-seated waves are thought to have met on the far side and pounded the crust there. The converging energy fractured and uplifted the ground, shattering it into the jumble we see. Ejecta may also have rained down on the area, adding a layer of coarse, blocky material that enhanced the relief. The result is a landscape with no local impact crater to blame, yet with all the symptoms of violence delivered at long distance. There is a satisfying elegance in that explanation. One event writes two landscapes, the basin itself, with its rings and plains, and, half a world away, a field of broken stone set by focused echoes. Nature loves such symmetries. They turn the planet into a resonant instrument, struck once and ringing in more than one place. Other worlds offer variations on the theme. The moon has basins with antipodal disturbances. On Mercury, the clarity of the pattern and the scale of the weird terrain make the case vivid. If you wanted to teach the concept of shock focusing to someone who prefers pictures to equations, you could hand them a mosaic of Mercury's antipode and let their eyes do the calculus. The influence of Caloris extends beyond its immediate rim and its far antipode. The sprays of ejecta and the subsequent volcanic flooding have set local baselines for what young and old look like on Mercury. Where a ray from a relatively fresh crater crosses Caloris lava, you know the sequence. The basin formed, lava flowed, and later the smaller crater arrived to chalk its streak across the pavement. Where a lobate scarp, a cliff created by global contraction, cuts the basin's plains, you can date the scarp as younger than the lavas it offsets. In this way, Caloris serves as a timepiece. Its features cross-cut and overlay others in patterns that, when traced carefully, let geologists build a timeline more intricate than simple crater counting can provide. Even the colour subtlety of the basin floor tells a story. Caloris interior plains often show a distinctive hue in calibrated images, different from the darker, older intercrater terrain outside. Those tonal differences, tied to composition, suggest that the lavas that flooded the basin were not merely remelts of local crust, but drew on magmas with their own chemical character. That in turn hints at Mercury's interior, its degree of differentiation, its lingering heat, its capacity to feed eruptions long after the basin formed. A single giant impact thus opened not only a hole in the surface, but also a window into the planet's kitchen. What does it feel like to imagine standing near the rim? The mountains would not rise like a continuous wall, but as a series of ridges and peaks, battered and faceted, their silhouettes serrated against a black noon sky. The ground underfoot would be a mix of breccia, rock made of rock fragments welded together by heat, and more coherent blocks with the occasional smoother expanse where later lava had crept up to the foot of the hills. Step inward across the basin floor and you would walk from roughness to smoothness, from impact architecture into volcanic paving. If you followed one of the troughs of Pantheon Fosse, its shallow depression would guide you like an ancient road until it faded into the broader plain, its edges defined more by shadow than by slope. Half a world away in the weird terrain, the mood would be different. There the hills pile like sleeping animals, and the spaces between them twist without right angles. It is a landscape designed by a hammer and a ripple, not by the steady hand of weather. You could climb a short rise and see that no obvious crater sits at the centre of the confusion, a clue that the cause came from elsewhere. And if you could switch to a planet-size view, the line from Caloris to its antipode would become obvious. Strike here, shatter there, ring upon ring, and then a far-off jumble. Caloris, then, is not simply a large feature, but a teacher. It shows how impacts shape crust at global scales. It reveals how a planet responds after the cataclysm, through volcanism that smooths and tectonics that crack. It demonstrates that energy can take long paths through rock and still leave a mark. And it reminds us that even in a place without air, without rain, without the busy chemistry of life, there is drama and aftermath, cause and echo, wound and healing. The basin's name means heat, and though the heat of its making has long since bled away into space, the story it began still warms the imagination. A single strike, a world that rang, and a surface that remembers. Mercury wears its age as a network of creases. Cross its plains and you meet great curving cliffs that step the ground down in graceful arcs, their backs rounded and their faces steep, like the fold of a thick rug pushed from one side. These features, lobate scarps, are the signatures of a planet that has tightened over time. They are not the scars of impacts or the edges of lava flows. They are faults, long thrusts where one slab of crust has ridden up over another, because the whole world has been trying to fit into a slightly smaller shape. The idea is simple enough to hold in the palm of your mind. Planets are born hot. Collisions during formation of violent furnaces, radioactive elements simmer within, and large metallic cores hold heat the way an iron kettle holds warmth after the fire goes out. Over billions of years, that heat leaks to space. As the interior cools, it contracts. If a planet has no system for sliding and recycling its surface, no plate tectonics, no global conveyor belt, then the outer shell must take up the slack by crumpling. On Mercury, which is small and metal-rich, the crumpling registered as global compression. The crust shortened like a drying fruit's skin, and the result was a web of lobate scarps that run for hundreds of kilometers and rise to heights of hundreds of meters, sometimes more than a kilometer. Under low sun, their shadows draw clean calligraphy across the ground. You can read their sequence with a little practice. A scarp slices straight through the rim of an old crater, offsetting the circle and making a neat chord where the rim once closed. That tells you the faulting happened after the impact. Elsewhere, a scarp crosses a smoother, younger plane and drops one side, its debris apron still relatively fresh and unsoftened by countless micro-impacts. That suggests the compression continued late in Mercury's story, not just in a single ancient spasm, but as a long, patient tightening. The crisscrossing relationships let geologists build a relative timeline. First a basin forms, later lavas flood its floor, later still a scarp kinks the plane, a quiet, orderly ledger of forces you cannot see. Why did Mercury shrink more than other rocky worlds? Part of the answer is that Mercury is built unusually. It is the smallest planet, but inside it houses an outsized iron core that swallows most of its volume. Imagine a world that is, proportionally, more kettle than crust. Metal contracts significantly as it cools, and when so much of a planet is core, even a small fractional change becomes a large absolute change. The rocky shell above, comparatively thin, had to accommodate that change by shortening. Without plates to shuffle sideways, shortening became thrusting, and thrusting became scarps. Mercury's location and history likely compounded the effect. Close to the Sun, it may have formed from ingredients depleted in lighter elements, or it may have been struck early by a collision energetic enough to strip away some of its outer rock, leaving the metal-rich interior dominant. However the starting recipe was set, it produced a planet that retained heat stubbornly in its centre and cooled enough to contract substantially in its shell. Add to that the rhythmic tidal flexing from the Sun's gravity, a daily kneading that over ages can help dissipate energy, and you have a world predisposed to wrinkle. Stand, if only in imagination, at the crest of one of these faults. The upthrown block under your feet forms a rounded back slope, and just beyond, the ground drops in a tidy step into a lower plane. At the base of the scarp, broken blocks have slumped into a wedge of rubble. Follow the cliff's trace and it bows and snakes for great distances, sometimes disappearing under younger deposits, sometimes re-emerging like a buried rope pulled taut. Where several scarps run roughly parallel, the terrain looks pleated, each fold catching light differently as the sun crawls across the sky. It is geology in a soft register. No smoking volcanoes, no churning seas, only the patient grammar of stone under stress. The comparison to the moon is instructive. The moon also has lobate scarps, evidence that its interior cooled and contracted, but they are fewer and generally smaller. Earth, by contrast, hides global contraction by letting plates wander, collide, and recycle. Our shortening shows up as mountain belts along plate boundaries rather than as planet-spanning thrusts that ignore older landmarks. On Mercury, the compression is planetary in scope and largely unchanneled by plate boundaries. The shell buckled wherever it needed to, often in long arcs that pay no attention to crater rims or flow fronts, except to offset them politely on the way through. In photographs, you can watch a scarp turn a perfect circle into two offset semicircles, like a coin pinched between finger and thumb. The amount of shrinkage can be phrased modestly and still feel immense. Mercury's radius has decreased by several kilometers since its outer shell solidified. That is enough to crumple a sphere. Picture a hard-boiled egg cooling and tightening under a brittle shell. The shell can only respond by cracking, sliding, and overlapping. The lobate scarps are those overlaps on a grand scale, the outer lithosphere pushing up and over itself as it tries to wrap a smaller volume. When spacecraft mapped more of Mercury at higher resolution, the census of scarps grew, and with it estimates of total horizontal shortening, a measure of how much the crust has scrunched in on itself. These cliffs are more than scenery. They are probes of the interior. The spacing and size of scarps tell us about the thickness and strength of Mercury's lithosphere at the time of faulting. A thin, warm shell would wrinkle into closely spaced, gentle folds. A thick, strong shell prefers widely spaced, taller faults with larger throws. By tying scarp relationships to surface ages derived from crater counts, scientists can sketch how the lithosphere thickened over time as the planet cooled. That cooling matters for another reason. Mercury has a magnetic field, weak but real, which requires a moving, electrically conducting fluid in the core, a dynamo. The coexistence of youthful-looking scarps and a lingering magnetic field paints a picture of a planet whose outer shell has been stiffening while, deeper down, liquid metal still circulates enough to wind magnetic lines. Cooling then is doing two jobs at once, tightening the skin and stirring the heart. Look closely at where scarps run across different terrains, and you can see the crust's personality show through. Crossing a rough-into-crater plain, a scarp can be jagged, with many breaks where older blocks influence the fault's path. Crossing a smooth volcanic plain, it may draw a cleaner, more sinuous line, with its displacement distributed more evenly through a homogeneous layer. In some places, instead of a sharp break, the plain is folded into a low-wrinkle ridge, a more ductile response where rock deformed without a single dominant fault. Such contrasts help distinguish where lava once pooled from where ancient ejecta lie thick, and they hint at how temperature and composition varied from place to place when the compression wrote its lines. There is a quiet satisfaction in how these pieces fit together. The oversized core explains the degree of contraction. The contraction explains the prevalence and scale of the scarps. The scarps, in turn, help time the cooling, which supports the idea of a still-functioning dynamo. And the dynamo closes the loop by reminding us that Mercury is not geologically dead in every sense. Its interior has not frozen entirely. The planet's great iron heart continues faintly to move. For human senses, tuned to weather and water, Mercury's style of change feels austere. Yet the lobate scarps make that austerity beautiful. They are clean, comprehensible structures, the kind that light loves. At low sun, their shadows draw piano string lines across the plains. At high sun, they soften and nearly vanish, letting other textures speak. In the long dawns and long dusks of a Mercurian day, the cliff's relief emerges and recedes slowly, so that you could sit with one for hours and watch the shade deepen like ink. They are proof that a world can be dynamic without storms and dramatic without noise. They also change how we read every other feature. A basin rim offset by a scarp reveals not just the order of events, but the stresses that once ran through the crust. A volcanic plain cut by a fault suggests that the interior was still cooling and contracting after the last significant eruption ceased. Even small craters perched on a scarp's face tell you that faulting did not sterilize the surface. Impacts continued, as they always do, writing tiny new notes atop the larger chords. And beneath all of this is a simple resonant story. Mercury is a compact world wrapped around a large metallic core. Over time, the core cooled and drew inward. The rocky shell could not stretch, it could only shorten. The shortening made cliffs, the cliffs made a map of invisible forces. That map is not only scientifically useful, it is quietly moving. It shows a planet aging with dignity, its lines earned honestly by physics and patience. If you trace one of those lobate arcs with a fingertip on a photograph, you are following the edge where one piece of Mercury climbed over another, so that the whole could stay whole. A tiny world composing itself into a slightly smaller, still coherent form around an iron heart that continues to hum. On Mercury, the sun does not simply rise, it accumulates. Light gathers for days, then weeks, climbing the crater rims grain by grain, until noon arrives like a kiln door opening. In full sunlight, the ground bakes until rock itself radiates fiercely. And when the sun finally drifts away, the heat bleeds back into space with nothing to slow it. Step a few meters into deep shadow, and the world becomes a freezer. This is the first lesson of Mercury. Day and night are not moods but regimes, and the passage between them is a slow migration of light across a landscape with no air to soften the contrast. An atmosphere is a grand negotiator. On Earth, air and oceans ferry warmth from place to place, trading heat between noon and midnight, between equator and pole. Clouds reflect sunlight. Greenhouse gases hold some of the planet's infrared glow close for a while. Even a windless evening wraps the ground in a thin blanket that slows cooling. Mercury has none of this. Its air is a wispy exosphere, a few atoms here and there, so thin that they seldom collide. Heat therefore moves by radiation, and by conduction within rock, not by convecting air. In sunlight, the surface soaks up energy directly and glows in invisible infrared until it reaches a balance. In darkness, it radiates away what it stored, dropping to deep cold because there is no blanket to hold the warmth. The same cliff can host both climates at once. A face turned to the sun is an oven door. A face turned away is a wall of ice. Time amplifies the extremes. A solar day on Mercury, a noon to noon, lasts 176 Earth days. Imagine dawn stretching over many Earth weeks, a blade of sunlight creeping across stones while the stars remain crisp in a black noon sky. Rocks under the sun have a long, patient time to absorb energy. Rocks in shadow have a long, patient time to surrender it. Because heat travels slowly within rock, the first few centimeters do most of the temperature swing, while deeper layers lag behind. That is why a thin overhang can offer meaningful refuge. A sliver of shade protects a shallow skin that would otherwise scorch. Without air, the boundary between hot and cold is a map drawn by geometry. Every boulder throws a private night behind it. The foot of a ridge hosts a narrow band where temperature sits between extremes, marching with the terminator, the line that divides day from night, as it creeps across the ground. Engineers dream about habitats that surf that line, keeping within the mildest possible zone by moving with dawn or dusk. The romance fades when you remember the terrain, crater rims, tailless ridge plains. The planet offers no highways, only the strict choreography of light. If the story ended there, Mercury would be a world of fire on one side and cold on the other, with a stripe of survivable dawn in between. But there is a second act, and it plays at the poles. Mercury's axis is almost upright with respect to its orbit, tipped by only a whisper. The sun therefore skims low on the polar horizons, never climbing high. In some craters near the poles, the floors lie so deep that sunlight never reaches them at all. These places are called permanently shadowed regions, and they are colder than any sunlit surface on Earth. They are cold not for minutes or days, but for millions of years. In such deep freeze, volatile substances that would otherwise sublimate into space can collect and persist. Decades ago, Earth-based radar began to hint at something peculiar in those polar craters. Observations from giant radio telescopes saw patches that reflected radio waves in a way characteristic of clean, coarse ice. Unusually bright returns with a telltale polarization signature. The bright spots were tucked inside the expected shadows, exactly where the sunlight never falls. A paradox was born, and it was a beautiful one. On the planet nearest the sun, there appeared to be ice. Skepticism was healthy. Could rough rock mimic the signal? Could metallic minerals produce similar reflections? The case improved when the spacecraft Messenger arrived. It mapped Mercury from orbit, carrying instruments that could test the radar's hint with different sensors. A laser altimeter traced the topography of polar craters with exquisite precision, confirming which floors were truly in permanent shadow. A neutron spectrometer felt for hydrogen, a proxy for water. By counting the way cosmic rays split atomed in the soil and how the resulting neutrons were moderated. Where the radar had said bright, the neutron spectrometer said hydrogen-rich, and the geometry said forever dark. In some places, the skin just beneath the surface appears to be loaded with water ice to depths of tens of centimeters, and in others a thin, darker layer, perhaps organic rich material or space-weathered crust, may cap and insulate a brighter, icier deposit below. How did the ice get there? Delivery and housekeeping. Comets and certain asteroids carry water and other volatiles. When they strike Mercury, some fraction of that cargo is vaporized and lofted. On an airless world, molecules released near the surface follow ballistic arcs, hopping along until they either escape to space or fall into a trap. The coldest traps are the permanently shadowed regions at high latitudes. Over millions of years, a slow drizzle of molecules from impacts and perhaps from the decay of hydrated minerals in the crust can accumulate in those freezers. The layer may be patchy, interrupted by subsequent impacts or by landslides, but the overall effect is a quiet migration of water to places where sunlight never reaches. Messenger's data also suggests that some deposits are very clean and bright, tall, nearly pure ice at the surface, while others are buried under a darker mantle a few decimeters thick, perhaps made of organic residues cooked into tarry films by radiation. The dark cap acts as a duvet, protecting bright ice beneath from stray warmth that might reach even into shadow. The presence of ice on Mercury is not merely a curiosity, it is a laboratory. It teaches how volatiles move on airless bodies and how microclimates can exist without air. It links to similar cold traps on the moon's poles, where spacecraft have also found water ice. And it reminds us that too close to the sun is a verdict written in broad strokes. Reality always has our corners where the rules find exceptions. In one place, an equatorial crater rim is a strip of annual furnace. In another, a polar crater floor is a vault of ancient frost. Same planet, different geometry, different fates for the same molecule. The extremes even shape chemistry in places far from the poles. Under long bombardment by sunlight and by the solar wind's charged particles, Mercury's surface loses some of its more volatile elements from the topmost grains. Over ages, that gentle distillation can change reflectivity and colour, and it may help create and then maintain those strange shallow depressions called hollows, where bright, fresh-looking material surrounds pits that lack raised rims. The day-night swing, repeated for eons, is not just a thermal spectacle, it is a chemical engine in slow motion. There is a kind of humour in how the smallest comforts become treasures under such conditions. A natural overhang that throws a ribbon of shade during the long noon would be prized real estate. A light-toned boulder that reflects more sunlight than its neighbours could serve as a radiant cooler of sorts for anything tucked behind it. At a pole, a ledge with a line of sight to the sun could catch power, while its floor stays forever cold a few metres away. The planet is stingy with moderation, but it is generous with edges, and edges can be used. Numbers are not required to feel the severity of the hot side and the cold side, but they help set the scale. In full high sun, Hot can climb to temperatures of over 400 degrees Celsius, hot enough to soften solders and scorch most materials. In deep shadow, temperatures can sink below minus 170 degrees Celsius, cold enough to make metals brittle and to sequester water into ice that will not sublime for geological spans. If that sounds contradictory, oven and cryogenic lab on the same street, that is exactly the point. Mercury is a place where opposites live shoulder to shoulder, divided by the simple fact of where the sun can and cannot reach. If you listen closely, the chapter resolves into a poem of physics. Heat arrives by radiation, not by air. Cold is an absence of incoming light, not a gust of northern wind. The poles are freezers because the planet barely nods to the seasons. Ice survives because geometry grants shadow that lasts longer than any human memory. The equator sears because the sun lingers and because nothing convects the energy away. And through it all, there is silence. No sizzling, no cracking frost, no sigh of breeze to comment on the contrast. Only light and stone taking turns. For future explorers, the paradox becomes practical. Sunlit slopes offer power in abundance. Shadowed pits offer resources and stable low temperatures. It is not hard to sketch a polar outpost carved into a crater wall, with solar arrays catching the grazing sun above and storage tanks nestled in cold chambers below. The same world that seems hostile becomes, with the right geometry, a cooperative partner. The planet nearest the Sun teaches gently but firmly that extremes are not noise, they are structure. Day and night on Mercury are not equal halves separated by a narrow line, but two profound states with a complex seam. In that seam, life, or at least machinery, could find a rhythm. And in the corners where light never arrives, ancient water keeps its counsel, a quiet archive of impacts and time, glimmering invisibly in a darkness as permanent as any place in the solar system can offer. Silence on Mercury is not simply the absence of noise, it is the consequence of physics. There is no air to carry a whisper, no wind to rattle a pebble, no distant thunder to roll across crater walls. Above the ground there is not an atmosphere but an exosphere, a veil so thin that its atoms almost never collide. Each particle is a solitary traveller, hopping in a long arc and then either falling back or slipping away to space. If you could bottle a cubic metre of Mercury's air, you would find far fewer atoms than in the best laboratory vacuum. It is a world where space begins just above your head. This fragile exosphere is made, unmade and remade continually. The Sun floods Mercury with light and particles. Tiny meteoroids sprinkle it with high-speed dust. The planet's surface itself releases atoms when struck or warmed. Three processes dominate. First is photon-stimulated desorption. Sunlight knocks loosely bound atoms off the topmost grains of rock, the way gentle taps dislodge dust from a shelf. Second is thermal desorption. Heat bakes atoms free during the long Mercurian day. Third is soterring. The solar wind, a stream of energetic charged particles from the Sun, slams into the surface and physically ejects atoms the way sandblasting frees grit from paint. Micrometeoroid impacts add a fourth sporadic source, vaporizing a pinch of rock and lofting a brief cloud. None of these add up to weather, they add up to a shimmering, ever-replaced fringe. What atoms are we speaking of? Sodium and potassium are prominent, joined by calcium and magnesium, with traces of hydrogen and helium that are largely captured from the solar wind rather than native. Sodium in particular is the exosphere's show-off. When sunlight strikes sodium atoms, specific yellow wavelengths, the famous sodium D lines, pump them into excited states. Radiation pressure then pushes on those atoms, nudging them anti-sunward. The result is a faint, comet-like sodium tail stretching many millions of kilometers behind Mercury, invisible to human eyes but detectable with sensitive filters. From Earth, astronomers have imaged this tail as a subtle fan glowing at the sodium wavelengths after the planet slips away from the Sun in the evening sky. It is a little astonishing the first time you see such a picture. The smallest planet wearing a ghostly streamer like a miniature comet, its atmosphere literally blown downwind. Because the atoms travel without colliding, the exosphere has seasons that are not seasons in any earthly sense. When Mercury is near its closest approach to the Sun, sunlight and radiation pressure are stronger, the days are hotter, and sputtering can be more vigorous in certain regions. The sodium cloud grows and the tail brightens. When micrometeoroid streams, the dusty debris trails of comets, intersect Mercury's orbit, short-lived surges in exospheric density appear, an atmospheric meteor shower with no sky to light. Even the planet's 3-2 spin orbit rhythm leaves a fingerprint. Dawn terminators often show enhancements as fresh sunlit surfaces release atoms after the long night. The exosphere also dances with Mercury's magnetic field. Yes, the little planet has one, weak compared to Earth's, but strong enough to carve a miniature magnetosphere in the solar wind. Where that protective bubble is thinnest, near polar cusps, charged particles can funnel down and hammer the surface. Those impacts liberate atoms and loft them into ballistic paths, feeding the exosphere locally. Meanwhile, electric currents driven by the solar wind can tug charged dust or ions, changing where material lands again. It is a constant quiet exchange, Sun to surface, surface to space, space back to surface. Why does Mercury have only this wisp of air when planets like Earth and Venus support thick atmospheres? Mass, heat, and nearness to the Sun set the rules. First, Mercury is small with gravity too weak to hold on to light gases for long. Give a hydrogen atom a bit of energy and it can reach escape speed and never return. Second, Mercury's surface is roasted for weeks at a time. Heat speeds atoms, and faster atoms are more likely to escape. Third, the planet orbits right in the stream of the solar wind and in the full glare of solar ultraviolet light. Both tear at molecules and loft atoms from the surface. If the young Mercury ever had a denser atmosphere, the Sun and the planet's modest gravity were an efficient pairing of thief and open door. Over time, the gas is left, and what remains is a near vacuum in perpetual turnover. That absence shapes everything you would perceive. The sky is black at noon because there is nowhere to scatter blue light. Shadows have edges so crisp they look drawn with a technical pen. Heat does not travel by convection, so there are no breezes to even out temperature. A spot in sunlight can be blistering, while a nearby patch in shadow is bitter. There are no clouds to paint the horizon, no hazes to soften distant ridges. Sightlines run as far as topography allows. If a boulder tumbles, it does so in silence, sending up a puff of dust that falls in pure ballistic arcs, each grain following its own neat parabola. Sound requires a medium, Mercury provides none. The silence is not emptiness, it is a different kind of activity. Space weathering, the slow alteration of surface grains by sunlight, solar wind and tiny impacts, changes colours and chemistry. Sodium and potassium are knocked free, migrate as solitary atoms, and either escape or fall elsewhere. Calcium pops off during micrometeoroid hits, producing brief hot clouds that cool and fade. Hydrogen and helium atoms from the solar wind bounce off the surface like hail on hard ground, sometimes sticking for a heartbeat, sometimes skipping away. Each event is microscopic. Their sum over eons is the patina we see from orbit. This airless world even has a faint glow, though not the kind you would notice with an eye. Under certain conditions, atoms returning to the ground emit light at their characteristic wavelengths. Against a black noon sky with the sun blazing, that glow is drowned, but with clever instruments it can be teased out, giving scientists a way to map where atoms prefer to come and go. Those maps show dawn-side enhancements, cusp region hotspots, and polar peculiarities tied to the cold traps where water ice lurks beneath dark mantles. It is meteorology reduced to its minimalist essence. No pressure fronts, no humidity, only source and sink. If you are fond of engineering puzzles, Mercury's lack of atmosphere is both a problem and a gift. There is no air to breathe or to shield you from radiation, so habitats must provide their own pressure and protection. There is no drag to help a lander slow down, rockets must do all the work. But there is also no weather to confound solar panels, no storms to bury equipment, and no corrosive winds to sandblast mirrors. The sun and the solar wind already do enough of that on their own. Communications are clean, horizons are honest, and a structure built into rock can rely on vacuum to keep heat transfer mostly to radiation, a challenge that can be turned into a design principle. At the poles, where sunlight grazes and shadow is permanent, the exosphere's scarcity becomes an asset. Cold traps stay cold because nothing carries warmth to them. The sodium tail, delicate as it is, offers a human-scale bridge to all this. It is one thing to say Mercury has an exosphere. It is another to point a specialized telescope and watch a yellow fan streaming from an entire planet, renewed day after day by nothing more than sunlight, heat, and the steady breath of the solar wind. It is a reminder that atmospheres are not a simple on-off property. Between Earth's dense air and the Moon's near-nothing lies a spectrum, and Mercury sits toward the nothing end, making dynamics legible one atom at a time. There is a gentle irony in how the planet nearest the Sun has winds of a sort, not in air, but in ions and radiation. Those invisible rivers shape the exosphere, stir the sodium, and etch the surface grain by grain. Yet to human ears and skin, the world remains perfectly quiet. You could place your hand on warm stone and feel heat without hearing a hiss. You could watch a meteor strike over the horizon, sense its aftermath only later as new atoms drift and a bright patch appears in a specialized image. The drama is real, but it is conducted in mime. In the end, Mercury's world without air is not an absence to be apologized for, it is a clarity to be appreciated. Without a sky, light behaves as geometry. Without weather, landscapes keep their lines. Without sound, time seems to move in longer units, dawns that last for weeks, exospheres that rebuild each morning, tails that wax and wane with an orbit's breath. The messenger planet remains a messenger still, delivering a simple lesson in 1,000 variations. You do not need a thick atmosphere to have a story. You only need light, rock, and the quiet patience to watch atoms come and go. If you could slice Mercury like a cake, you would find that most of it is filling and very little is frosting. Beneath a comparatively thin shell of rock lies an enormous heart of metal, an iron-rich core so large that it takes up the lion's share of the planet by both radius and mass. Mercury's overall radius is a little under 2,500 kilometers, and the core is thought to span roughly 4/5 of that distance. By mass, something like 2/3 to 3/4 of the entire planet is metal. For a rocky world, that is extravagant. Earth has a big core, yes, but most of Earth is still rocky mantle. Mercury is the opposite, a compact sphere built around a gleaming centre. You can feel that metal indirectly through the planet's numbers. Mercury's bulk density is high, more than 5 grams per cubic centimetre, and when you correct for the fact that small planets are less compressed by their own gravity than big ones, Mercury still comes out unusually dense. Another clue comes from the way the planet spins and wobbles. Precise tracking of its rotation and tides gives a moment of inertia that tells you how mass is distributed inside. For Mercury, that value says the heavy stuff sits very deep and very centralized. The way the surface flexes under the sun's pull, a quantity with the charming name love number, adds that at least part of the core must still be liquid. The result is a portrait of layers, a solid inner core, a liquid outer core, perhaps a thin dense layer rich in sulfur at the core mantle boundary, and then a relatively meagre mantle and crust riding above. How did a planet end up so metallic? Nature offers a small menu of origin stories, each plausible in part and none yet the full answer. One is the giant impact diet plan. A proto-Mercury larger and more Earth-like in proportions suffers a massive collision that strips away much of its rocky mantle, leaving behind a core-heavy survivor. That idea explains the metal, but it must be tuned carefully so that Mercury is not robbed of all its volatile elements in the process. Measurements from orbit found surprising amounts of sulfur and other relatively volatile ingredients in Mercury's crust. Those do not sit easily with the scenario in which everything was blasted and boiled away, so if a big impact did the sculpting, it likely involved hit-and-run geometry and rapid removal of the debris before it could fall back, with enough gentleness in the surviving surface to keep some of the chemistry intact. Another idea shifts the blame to the young sun. Close to the star, temperatures in the early solar nebula may have been high enough that rocky silicates struggled to condense, while metals like iron could do so more readily. In that chemical sorting, inner regions of the disk might have fed a metal-rich diet to bodies, forming very close in. Variants of this story invoke photophoresis, sunlight pushing small grains differently depending on their properties, or magnetic effects that shepherd metal grains toward the centre. These ideas match the broad gradient of compositions we see across the solar system, but they also must contend with the same geochemical facts. Mercury's surface is not stripped of volatiles to the degree one might expect if it had baked mercilessly in a cosmic kiln. A hybrid picture may be nearest the truth. Start with a region of the solar nebula that already favours metals. Add collisions, not one catastrophic blow, but a sequence of glancing hit-and-run encounters that whittle away silicate mantle more easily than iron core. Let the sun's early tantrums, bursts of radiation and gusts of solar wind, help clear away the lighter debris before it can be reaccreted. You are left with a small world whose centre of gravity is, quite literally, its centre. Living above such a core changes everything about a planet's later life. With so much metal inside, Mercury hung on to internal heat longer than you might guess from its modest size. Metals conduct heat efficiently, and a large metallic volume cools slowly. That stored warmth, plus a little help from radioactive elements, allowed part of the core to remain liquid to this day. A moving electrically conducting fluid is the prerequisite for a planetary dynamo, the process that generates a magnetic field. Mercury's field is weak, only a small fraction of Earth's strength, but it is global and real. It is a soft hum compared to Earth's orchestra, yet it tells you that liquid metal still circulates in the depths. The big core also explains the surface's long-term wrinkles. As the interior cooled, it contracted. Rock cannot simply stretch to accommodate a shrinking interior, it breaks and shortens. Mercury's signature lobate scarps, those long curving cliffs that step the ground down by hundreds of meters, are the outer skin taking up the slack. In a sense, the cliffs you can trace from orbit are the biography of a cooling core written in stone cursive. Mercury's mantle, by contrast, is a study in restraint. On Earth, the mantle is deep enough and buoyant enough to circulate, to melt in places, and to feed a lively history of volcanoes and plate tectonics. On Mercury, the mantle is thin, perhaps only a few hundred kilometers thick, and it likely cooled into stiffness relatively early. That does not mean it was always quiet. The planet's smooth plains, which fill lowlands and basins with broad sheets of once molten rock, tell of an era when magma could still make the journey upward. Those floods appear to have been extensive in places, especially inside large impact basins like Caloris. But the volcanism waned and the world's energy turned increasingly inward, contracting and settling rather than erupting. Chemistry at the surface echoes the deep story. Observations from orbit revealed a crust rich in sulfur and other elements that prefer a reducing environment, one with less available oxygen. That chemical fingerprint suggests Mercury's interior formed and evolved under conditions different from Earth's, with iron bonded to sulfur in the core and with iron-poor silicates in the mantle. Some models even propose a thin layer of iron sulfide perched at the base of the mantle, a dense lid between rock and liquid metal that could influence how heat escapes and how the dynamo behaves. The same chemistry might explain one of Mercury's stranger small-scale features. The hollows, fresh-looking shallow pits, often ringed by bright material. They appear where volatile-bearing minerals at the surface are exposed to fierce sunlight and the solar wind, losing their more delicate components and leaving Swiss cheese-like textures behind. A world born metal-rich and oxygen-poor ends up with minerals that, under the right provocation, can simply vanish into space one molecule at a time. The metallic heart sets the stage, the sun supplies the patient chisels. It is tempting to think of a metal-heavy world as dour and inert, but the opposite is true. Metal gives Mercury memory. The core's slow cooling keeps the dynamo alive. The dynamo shapes a magnetosphere that, though small, sculpts the flow of particles around the planet and funnels bursts of energy onto the surface at the polar cusps. The core's contraction tightens the crust into cliffs that you can map like wrinkles on a thoughtful brow. Even the way impacts ring the planet, sending shockwaves through a metal-rich interior, may differ in subtle ways from rockier worlds, perhaps contributing to the dramatic, weird terrain opposite Caloris, where focused waves once shook the ground to pieces. For all its physics, Mercury's metallic heart also has a kind of poetry. Picture a sphere where the boundary that matters most is not the horizon you see, but the horizon you cannot. The core mantle boundary thousands of kilometres below, where liquid metal laps against stone. Above it, a thin rocky rind carries the scars of bombardment and the curves of contraction. Below it, a heavy gleaming ocean of iron alloy turns slowly, whispering magnetism into space. The planet is small, but its centre is grand. What does "how much of the planet is metal" really mean for its history? It means formation close to the Sun was not a simple copy and paste of Earth in miniature. It means the early solar system did not mix its ingredients evenly. Distance, temperature, magnetism and violence all sorted the pantry in their own ways. It means that the same processes that built Earth into a blue world built Mercury into a dark stone wrapped around an iron bell, and that both results are natural outcomes of one disk of dust and gas cooling and colliding under a young star's glare. And it means that when you look at Mercury through a telescope and see a modest point of light near the horizon, you are, in a sense, looking at a core with a planet attached. That is not an insult, it is a compliment. Few worlds wear their essential nature so honestly. The messenger's message from this chapter is straightforward. Sometimes the heart really does define the whole. When the spacecraft Mariner 10 swept past Mercury in the mid-1970s, scientists expected a quiet world and straightforward measurements. What they did not expect was a magnetic surprise. As the probe crossed the dayside and slipped into the planet's shadow, its magnetometers twitched in a pattern that looked suspiciously like a planetary magnetic field. Not a passing gust from the Sun, not a glitch, but the signature of a magnetosphere wrapped around the smallest planet. The reading was modest, only a whisper compared with Earth's storm-tested roar, yet it was unmistakable. Mercury, airless and compact, carried a global magnetic field. That discovery unsettled a neat story. Planetary dynamos, the engines that generate magnetic fields, are usually the province of big worlds with heat to spare. Earth with its churning iron core, giant planets with metallic hydrogen, even the Sun itself with boiling plasma. Small bodies cool quickly and tend to fall silent. Mercury apparently had not. The immediate question was, how? To understand why this was puzzling, imagine what a dynamo needs. First, you require a fluid that conducts electricity. Second, that fluid must be moving, ideally in complex, spiraling patterns. Third, there must be an energy source to keep the motion going over geological time. Heat leaking outward, material separating and releasing buoyant light elements, or both. On Earth, the recipe is a liquid iron outer core stirred by heat and by the growth of a solid inner core that expels lighter elements into the fluid, driving convection. Mercury, however, is small. If it cooled as quickly as a simple model would suggest, its core should have largely solidified long ago, shutting down the fluid motions that sustain a field. Mariner 10's flybys did not hang around long enough to sketch out all the details, but they set the terms of the riddle. The field was dipole-like, think bar magnet, and weak, roughly 1/100th of Earth's at the surface. It was centred on the planet, so it looked intrinsic rather than a mere temporary effect of the solar wind. That alone was remarkable. Some suggested that Mercury's magnetism might be an illusion of crustal rocks carrying a remnant field, the way some lunar regions preserve ancient magnetization. But a global organised magnetosphere is hard to fake with patchy crusts. The simplest explanation kept reasserting itself. Mercury had a dynamo, and therefore it must have liquid metal moving in its depths. Decades later, the Messenger spacecraft settled the argument and added rich nuance. By orbiting Mercury for years, it mapped the magnetic field in detail and measured how the field changed as the sun's gusty influence varied. The field proved lopsided. The dipole was shifted northward by a noticeable fraction of the planet's radius, so that magnetic strengths in the northern hemisphere differed from those in the south. That offset hinted at structure within the core, perhaps a stably stratified layer, suppressing convection in one region, or differences in how heat escapes into the overlying mantle. Messenger also watched Mercury's magnetosphere snap and reform as magnetic reconnection. The linking and unlinking of magnetic field lines played out briskly on the day side. The little magnetosphere is a lively place, buffeted by the solar wind and attached to a long magnetotail that stretches away from the sun, waxing and waning with each gust. The very existence of a field told a second, quieter story. Part of Mercury's core remains molten. Independent lines of evidence agree. The way the planet flexes under the sun's pull, the details of its rotational wobble, and its response to changing solar fields all point to a large, electrically conducting liquid inside. Most models picture a solid inner core surrounded by a liquid outer core, rich in iron and sulfur, with perhaps a thin, even denser layer of iron sulfide perched at the base of the mantle. That compositional detail matters. Sulfur lowers the melting point of iron, allowing liquid to persist at temperatures where pure iron might freeze. It also provides a source of compositional buoyancy. As the inner core grows, it leaves behind sulfur-enriched liquid that is lighter and rises, stirring the outer core and helping to power the dynamo. Even with that help, sustaining motion in a small world is not trivial. Heat must escape at the right rate. Too fast and the core freezes, too slow and convection stalls under a blanket of warm, stratified fluid. Mercury seems to have threaded that needle. The planet's mantle is thin, so heat has fewer kilometers of rock to traverse before it radiates to space. But the presence of a sulfur-rich layer at the core mantle boundary may insulate unevenly, guiding where and how the core can cool. Add the slow release of latent heat as the inner core crystallizes, and the buoyancy from light elements being expelled, and you have a plausible energy budget for a gentle, long-lived dynamo. Messenger offered yet another clue by finding that parts of Mercury's crust carry faint, stable magnetization. That suggests the planet had a magnetic field far in the past, when those rocks cool through temperatures at which magnetic minerals lock in a preferred direction. In other words, the dynamo is not a recent flare-up. It has been present, off and on, or perhaps continuously at a low murmur, for billions of years. The longevity in the chapter title is not hyperbole. A tiny world has kept its iron ocean moving long past the time. Simple cooling arguments would have assigned to silence. At the surface, the field's influence arrives in flashes rather than breezes. There are no auroras to see with human eyes. There is no sky to paint. But the magnetosphere funnels charged solar particles into polar cusp regions where they slam into the ground and knock atoms free. Those atoms, sodium, potassium, calcium, join the exosphere in brief local blooms that sensitive instruments can detect. Magnetic reconnection on the day side opens the shield and lets bursts of energy in. The magnetotail stores energy and releases it in tailward bursts. Compared with the Earth, everything is smaller, faster, closer to the engine. The space weather is a mime performance played on a miniature stage. If Mercury's dynamo is so weak, why not simply call it fading and be done? Because its structure is too interesting to be a mere dying ember. The northward offset of the dipole, the relative weakness of high-latitude crustal magnetization in the south versus the north, and the way the field responds to solar forcing all argue for an organized engine, not random leftovers. Something about the way heat leaves the core, perhaps cooler northern mantle rocks, perhaps an insulating chemical layer that is thicker in the south, is shaping the flow of liquid metal. In numerical experiments, dynamos can be coaxed into offset dipoles when the outer boundary conditions are asymmetric or when radial heat flow is uneven. Mercury seems to have built such a symmetry into its bones. Longevity then becomes less a paradox and more a lesson in details. Small worlds do cool quickly in general, but composition matters, boundary conditions matter, and the partitioning of heat between mantle and space matters. A core alloyed with sulfur can stay liquid longer. A thin mantle can let heat out steadily enough to keep convection gentle rather than explosive, provided there is no lid that throttles it entirely. The slow crystallization of an inner core can power motion for eons. If you adjust any of those knobs, the dynamo flickers, set them as Mercury did, and the flicker becomes a nightlight that never quite goes out. There is another kind of longevity encoded in the field: memory. Rocks that carry remnant magnetization are fossils of the dynamo's past moods. If a future mission were to measure those crustal magnetic patterns at low altitude with high precision, it could read a diary, when the field was stronger, whether it reversed, how its geometry evolved. Messenger took the first step in suggesting those records exist. The next step will be to read them in detail and tie them to the ages of the host rocks, which in turn tie back to the planet's impact and volcanic history. A magnetic field, then, becomes more than a shield or a curiosity. It becomes a timekeeper. For the listener settling into sleep, the metaphor is gentle. Inside this small, battered world is a slow ocean of liquid metal. It turns faintly under gravity's pull and heat's persuasion. It writes invisible lines into space that deflect charged particles and tug at sodium atoms in the exosphere. It is not strong enough to make auroras flare or compasses swing, but it is steady enough to say there is motion in the dark. Mariner 10 heard that whisper first. Messenger learned the melody, and now the puzzle of how long the tune has been playing Londorat, and exactly which instruments in the core keep the rhythm, remains one of Mercury's quiet gifts to planetary science. Perhaps that is the best way to hold the enigma. Mercury is small, yet its heart is large. It is close to the sun, yet it keeps a secret ocean cool enough to flow. It is quiet outside, yet inside it hums. A field that should not be there according to the simplest stories is there, shaped oddly, enduring patiently. In a solar system filled with grand performances, the smallest planet offers a recital in a minor key, persistent, technical, and unexpectedly beautiful. At first glance, Mercury looks like a world written entirely by impacts. Craters overlap like rings on a pond, basins sit within basins, and rays cross the plains in chalky streaks. But woven through that battered canvas is another story. Fire. Long before the planet settled into its current quiet, molten rock rose from within and spilled across the surface in sheets so broad that they softened the landscape, filled cavities, and paved over older scars. The result is a patchwork of volcanic plains, some smooth as poured syrup, some subtly ribbed, that tell of a time when Mercury was not only being struck from above, but also welling up from below. Think of flood lavas as planetary house paint applied with gravity's broadest brush. Instead of a tall cone growing around a persistent vent, as on many volcanic islands on Earth, Mercury favoured low, extensive eruptions that ran outward and pooled. You can see their signatures in the way certain lowlands are mantled with material of uniform tone, and in how those mantles lap against older, rougher terrain. Along the edges, the lava sheet sometimes curls into a gentle step, a flow front, where the last of the molten rock stalled and cooled. In other places, the lava crept through a breach in a basin rim and fanned across the floor, erasing earlier topography until only ghost rims peered through as faint rings. Under low sun, these plains gleam with a calmer texture than their surroundings, a glossy note in a rocky score. Inside the giant Caloris Basin, the case for volcanism is especially clear. The basin's interior is paved in places by smooth plains whose colour and chemistry differ from the older highlands beyond the rim. The plains embay isolated hills, bury sections of wall and display flow-like margins, all signs that magma erupted after the impact and took advantage of the low fractured ground. Caloris is not alone. Elsewhere across the planet, broad expanses of smooth plains fill ancient lows, suggesting that for a long stretch of time, Mercury's mantle still had enough heat and buoyancy to send melt upward, even though the mantle itself was comparatively thin. Volcanism on Mercury did not confine itself to floods. Scattered across the surface are shallow, rimless pits with aprons of unusually bright reddish-tone material, the footprints of explosive eruptions. These deposits look like wide halos splashed around source vents, rather than like the dense sheets of flood basalts. Their texture and colour imply pyroclastic activity, magma that reached the surface carrying gas, then burst into ash and glass that fell back in drifts. On an airless world, you might not expect fireworks, but volatiles dissolved in magma can drive explosive release even without atmospheric pressure. The deposit's freshness, crisp edges, vivid tones, suggest these eruptions happened after the Great Floods had done most of their work, extending Mercury's volcanic story by another chapter. Between the smooth volcanic plains and the explosive aprons lies an intermediate class of landscapes where lava quietly exploited weaknesses. Fractures radiating from basin centres, such as the web of Pantheon-like troughs inside Caloris, may have provided pathways. In some places, plains seem to have oozed up along fault-bounded depressions, spreading like batter in a pan. Wrinkle ridges cross parts of these plains, low sinuous swells that formed as the surface shortened gently after it cooled, a reminder that Mercury's interior was not only erupting, but also contracting over time, tightening the planet's skin while the last flows were still warm. If you walk this world in the imagination, you learn to read age in texture. The oldest intercrater plains are rough, pitted, and overlain by countless small craters. Younger volcanic plains are smoother and host fewer superposed impacts. A fresh, bright-rayed crater slaps its calling card across both, declaring itself youngest of all. Sometimes a lobate scarp, one of the planet's great contractional cliffs, cuts cleanly across a lava field, dropping a broad step into an otherwise level sheet. That cross-cutting says the scarp came later, after the volcanism cooled, as the big iron heart within drew inward, and the crust had to accommodate. Among Mercury's most intriguing volcanic companions are the hollows, small irregular rimless depressions that sparkle with bright, high reflectance material. They pepper crater floors, ring bright spots along central peaks, and even dimple some volcanic plains. Hollows are not impact features. They look as if patches of the surface have been scooped away or have sublimed out from within. The leading idea is that certain rocks on Mercury contain volatile components, perhaps sulfides or other easily lost ingredients, that when exposed by impacts or by tectonic fractures and then assaulted by harsh sunlight and the solar wind, can be driven off. As the volatiles leave, the rock loses cohesion and collapses into shallow pits, exposing fresh, bright faces that have not yet been darkened by space weathering. In several locales, hollows cluster within or beside deposits of unusually dark material that likely represent ancient carbon-rich remnants of a flotation crust or deep-seated low reflectance layers brought up by impacts. The juxtaposition hints at a chemical layering inherited from Mercury's early differentiation, layer edited by both volcanism and impacts, and now being sculpted grain by the sun. What kind of lavas built the plains? Clues come from colour, reflectance, and elemental measurements from orbit. Many plains are poorer in iron than typical terrestrial basalts, and richer in elements like sulfur. That chemistry fits a planet that formed under reducing conditions where oxygen was less available to bind with metals. Reduced magmas can be relatively fluid at eruption temperatures, favouring wide, thin flows that travel long distances, just the style of volcanism Mercury displays. The absence of tall composite cones and the prevalence of sheet-like deposits line up with that picture. Vents that fed out pourings rather than edifices that built upward. Timing is the quiet metronome beneath the scenery. Crater count dating suggests that the most extensive flooding happened early, during and after the era when large basins formed. As time passed, the volume and frequency of eruptions waned. Explosive deposits in some regions appear younger than the broad plains, implying that volatile-rich magma found pathways even after the Great Flood ceased. Eventually, however, volcanism dwindled to silence. The mantle cooled, the pathways froze. Contraction continued, but eruption did not. Mercury became, in a volcanic sense, a museum. Exhibits well lit by a patient sun, footprints preserved where lava once moved like dark water. That long silence has consequences you can see. A volcanic province on Earth would be revised by rain and frost, hidden by soil, or cut by rivers within a geological blink. On Mercury, the flows remain where they cooled, their margins still sharp in the right light. Wrinkle ridges retain their low relief. Explosive aprons, though gradually muted by micrometeorite gardening, still blush against darker surroundings. The hollows glitter with fresh brightness until they too are dulled by space weathering, at which point another patch nearby may begin to form as a new little pocket of volatiles is exposed. It is a slow theatre, but it never entirely stops. If you place yourself on the lip of a smooth plain at low sun, the sense of flood is unmistakable. The lava sheet stretches away in a shallow, shining plain, broken only by the low ridges and by islands of older highland that rise like stranded hills in a receded sea. The silence is complete. No wind rakes the surface. No surf chisels at the edges. Yet in that silence you can almost hear the past. The slow advance of molten rock, the gentle buckling as it cooled and shrank, the pop and hiss of gases escaping in explosive bursts that left cinnamon-hued aprons. Later impacts hammer in punctuation marks, exposing the bright subsurface and, in lucky locations, setting the stage for hollows to nibble their way across a crater floor. Volcanism's end does not mean the planet became boring. The scars of global contraction went on deepening, stepping plains down in tidy ledges. The magnetic field continued to hum, faint but orderly, guiding charged particles to the poles and helping to stir the wisps of exosphere. The polar cold traps collected their improbable frost. In that larger story, volcanism is an early movement, bold, sweeping, and then increasingly sparse, giving way to themes of cooling and tightening. But its traces shape how everything else reads. A ray that crosses a dark volcanic sheet has a different brightness than one that crosses rough intercrater terrain. A scarp that kinks a flow front tells you precisely the order of events in that neighbourhood. A hollow that bites into a pyroclastic apron says both chemistry and sunlight are still collaborating even now. Perhaps the most human-friendly way to hold all this is to picture Mercury's interior as a kitchen that once had the heat turned up high. For a long while the pot boiled. It spilled over the rim, and the stove received ladles of dark sauce spread thinly and widely. Then the flame dropped. The last spurts of steam blew out flourishes around a few vents, and the lid settled. Now the kitchen is cool. The spills remain where they dried, the sheen dulled by a fine dust that falls from an unending sky, and the occasional drop still evaporates here and there where the light is harshest. It is tidy, legible, and strangely beautiful. Volcanic Mercury is not a loud story of mountains building themselves skyward. It is a quiet story of sheets and halos, of chemistry and cooling. The plains say that the mantle could still deliver, long after the biggest impacts, and the hollows say that even a world of metal and stone keeps secrets in its minerals that sunlight can coax out. Then the world grows still. The last lava stiffens, the cliff lines lengthen, and the planet nearest the sun, once briefly a painter in blacks and reds, returns to its preferred palette of greys, a gallery where the brushstrokes endure for as long as light can trace them. The first time we truly met Mercury, it was at arm's length and on a tight schedule. In the 1970s, a slim spacecraft called Mariner 10 threaded a path that would change how we travel the solar system and how we see this small elusive world. Launched toward Venus first and then swung sunward, Mariner 10 was the pioneer of gravity assists, using a planet's motion and mass as a slingshot to bend and boost a trajectory. That clever trick turned a mission that could have been a single hurried glance into a sequence of 3 encounters: spring of 1974, autumn of 1974, and early 1975. With each pass, cameras and instruments woke for a few fevered hours, gathered what they could, and then Mercury slipped back into glare. What did those brief visits find? A face both familiar and startling. The images showed a surface that at first looked like the moon's elder cousin, cratered, ancient, pocked with basins and ringed mountains. There were bright rays splashed from fresh impacts, and there were dark, smoother expanses that flooded lowlands. But mixed into the scenery was something new. Long, swooping cliffs called lobate scarps, sweeping for hundreds of kilometers with their backs rounded and their faces steep. They cut across craters and plains alike, indifferent to what lay beneath. Their geometry told a quiet, profound story. The planet had shrunk. As the interior cooled, the outer shell had to wrinkle, and it did so by thrusting one slab over another. This was not a detail. It was a planetary confession carved into stone. Mariner 10 also carried magnetometers, and as the spacecraft skimmed the day side and arced into night, those instruments twitched and settled into a pattern that was impossible to ignore. Mercury had a magnetic field, not a little patch of magnetized crust, not a transient gust, but a global dipole, weak compared with Earth's but organized and real, strong enough to carve a tiny magnetosphere in the solar wind. That single measurement upended expectations. Small worlds are supposed to cool quickly and sleep. Mercury instead whispered of a liquid core still in motion. Between surprises, the probe gave us a map, incomplete, irregular, but precious. The geometry of the flybys and the relentless glare of the sun meant Mariner 10 could only photograph the same hemisphere under good light on each pass. It returned a detailed atlas of roughly half the planet, while the other half remained a silhouette waiting for a new mission and a different season. Within the mapped side, the camera traced intercrater plains roughened by eons of bombardment, and smoother plains that seemed to have flowed like dark water across lowlands. It glimpsed the edges of a gigantic basin whose full grandeur would not be clear until later. Caloris, a wound on a continental scale. Outside the basin, the ground lay textured in ridges and grooves aligned like ripples around a stone dropped in a pond. Ejecta frozen in lines that told the direction of violence. The spacecraft's ultraviolet spectrometer sampled the near-nothing that passes for air on Mercury and found helium and hydrogen. A sign that the planet's exosphere is replenished and eroded in a delicate balance with sunlight and the solar wind. At the time, sodium's grand comet-like tail had not yet been imaged from Earth. That would come later with specialized filters. But Mariner 10 planted the idea that Mercury's atmosphere is a verb more than a noun. Atoms coming and going, driven by light and by the slow rain of micrometeorites. The first maps were a gift with a sting. They answered and they teased. Which half of Mercury were we missing? Did the smooth plains really mean volcanism? Or could they be mostly impact melt? How extensive were those lobate scarps, and when did they form? Was the magnetic field a fading ember or something sustained by chemistry and heat deep within? Every image carried footnotes that read, "To be determined." That is the way of pioneering missions. They turn the unknown into questions precise enough to ask well. After the last flyby in early 1975, Mercury returned to being a spark in twilight for more than a generation. The unanswered questions did not sit idle. Observatories on Earth chased clues. Radar hinted at something bright in polar shadows. Telescopes traced sodium at specific wavelengths and found a faint, streaming tail. In laboratories and on blackboards, models took computed shape for how a small world could keep liquid metal flowing. Perhaps sulfur in the core lowering the melting point. Perhaps heat escaping unevenly through a thin mantle. And quietly, in the late 1990s and early 2000s, a new mission gathered itself piece by careful piece. MESSENGER, a delightful acronym for Mercury's Surface Space Environment Geochemistry and Ranging Mercury, launched in 2004 on a patient looping odyssey. To fall inward toward a sun-baked world without air, you must burn a great deal of fuel or be clever with gravity. The mission chose cleverness, 1 flyby of Earth, 2 of Venus, and then 3 of Mercury itself to shed speed and tune the path. Each Mercury flyby in 2008 and 2009 took fresh pictures of the uncharted hemisphere, adding slices to the map like pages torn from a book and laid in place. Finally, in 2011, engines fired and the spacecraft slid into orbit, beginning years of unhurried work that turned Mariner 10's collage into a globe. From orbit, the mysteries Mariner 10 left behind began to yield. The smooth plains, many of them were volcanic flood lavas, their margins marked by gentle flow fronts and their chemistry distinct from the surrounding highlands. Explosive deposits appeared as bright, cinnamon-toned aprons around shallow vents, proof that volatile rich magma had once burst into space even on an airless world. Lobate scarps multiplied in the new maps. They ran everywhere, through old craters and across young plains, confirming not only that Mercury had shrunk, but that the shrinking continued longer than many had guessed. The big basin glimpsed by Mariner 10 became a full portrait. Caloris, its interior partly paved with younger lava, its rim terraced and its exterior surrounded by lineated terrain. Half a world away, the Antipode showed a field of jumbled hills, the weird terrain where shock waves converged and lifted the ground into a fossilized shudder. Messenger weighed the planet with radio tracking, teased out the distribution of mass, and tightened the picture of a vast, partially liquid core wrapped in a thin mantle and crust. It flew magnetometers through every latitude and found that the dipole was offset northward, a lopsidedness that hinted at complex layers or uneven cooling at the core mantle boundary. It carried a neutron spectrometer, a laser altimeter that, together with Earth-based radar, closed the case on the polar paradox. In the deep cold of permanently shadowed craters, water ice hides, some of it bright and clean, some of it buried under a thin, darker insulating cap. The smallest planet closest to the Sun keeps frost in its long night. It also found features no one had put on the wish list. Scattered across crater floors and plains were those peculiar hollows, shallow rimless pits, often ringed by bright, fresh material. They looked young, and they formed where certain volatile-bearing rocks were exposed and then sculpted by sunlight and the solar wind. Mercury was not only a museum of deep time, In small, scattered ways, it was still changing. By the time Messenger's propellant ran out in 2015 and the spacecraft kissed the planet's surface at speed, Mercury had transformed from a half-seen riddle into a detailed world with a coherent story. The leap from Mariner 10 to Messenger was not merely one of resolution or coverage, it was a leap from "what does it look like" to "how does it work?" The first visitor taught us that Mercury is a place of contraction and magnetism. The second taught us how contraction wrote its map, how volcanism paved its lowlands, how ice can persist in a geometry of eternal shade, and how a small core can keep a field humming. There is still a certain romance in those original flyby frames. The lighting is stark, the craters cast long shadows, the edges of the unknown sit just off the limb, unphotographed, daring the next mission to fill them in. When you see Mariner 10's scarps for the first time, you feel the thrill of a fresh grammar discovered. Here is how a planet says, "I have tightened." When you see its magnetometer trace swing, you hear a faint music from a world that was supposed to be mute. And then, with Messenger, the score fills in, bassline, melody, counterpoint, until the little planet's tune is something you can hum. The story of the first visitors is, in the end, a story about patience and invention. A clever slingshot turned a single chance into 3. A second mission turned 3 glances into years of study. Along the way, Mercury reminded us that small does not mean simple, that near the sun does not mean empty of surprises, and that even a world with no air and no seas can be rich in questions worth asking. The messenger god lent his name to a planet. In return, the planet lent its name to a spacecraft that delivered exactly what the ancients imagined messengers deliver: news from a place most of us will never go, written clearly enough that we can read it in the quiet before sleep. Messenger arrived at Mercury like a patient cartographer, determined to turn a half-known face into a globe you could hold in the mind. Years of gentle spirals and flybys had trimmed its speed. A crisp burn slid it into orbit. And then, quietly, the work began. Where Mariner 10 had drawn an exquisite but incomplete portrait, Messenger set out to colour the entire canvas. Camera by camera, pass by pass, it stitched together a map of the whole planet. Bright rays like chalk strokes, dark plains like spilled ink, cliffs folded and in long arcs. Under changing sunlight, the surface revealed different truths. Low sun for relief, high sun for composition, the in-between for subtle boundaries. For the first time, Mercury was not a silhouette with secrets on the far side. It was a world unveiled in full. Mapping, though, was only the beginning. Messenger carried instruments that could weigh, sample, and sound the planet at a distance. A laser altimeter pinged the ground and measured the return to the microsecond, building a topographic model ridge by ridge and basin by basin. The result resembled a fossil sea with waves frozen in stone. The multi-ring outline of the Caloris Basin, the hummocks of jumble terrain at its antipode, the low, sweeping wrinkle ridges that quilt smooth plains after they cooled and tightened. The altimeter also traced the deep bowls at the poles where sunlight never arrives, drawing a shadow map that would soon prove surprisingly useful. The spacecraft's cameras did more than make pretty pictures. With filters that isolate specific slices of colour, they assembled mosaics in false hues that separate rock types by chemistry. In those palettes, Mercury's surface stopped being a uniform grey and resolved into a patchwork. Some terrains richer in magnesium and poorer in iron than typical terrestrial basalts. Others dusted with unusually dark material thought to be carbon-rich remnants from deep layers or early crust. Smooth plains took on consistent tones distinct from older highlands, supporting the case that they were not just pools of impact melt, but wide eruptions of lava that rose from below. Along some crater rims, delicate halos of warm cinnamon colour surrounded shallow vents, the fingerprints of pyroclastic eruptions where gas-charged magma burst and dusted the ground in glassy ash. Messengers, X-ray and gamma-ray spectrometers read the elemental ingredients straight from the surface. The crust turned out to be poor in iron yet rich in sulfur and other volatiles, a chemical signature of a planet that formed in a reducing environment, one where oxygen was scarce enough that metals and sulfur paired off readily. Potassium and thorium ratios defied the idea that Mercury must have been baked free of volatiles by the young sun. Somehow, despite its closeness to the star and despite whatever dramatic events sculpted its proportions, the planet held on to sulfur and other easily lost elements in surprising abundance. That chemistry reshaped origin stories. A single catastrophic blast boiling off everything light no longer fit well. Instead, ideas involving metal-friendly regions of the solar nebula and a sequence of glancing impacts gained traction. If the crust told a tale of chemistry, the gravity field told a tale of structure. By tracking tiny changes in Messenger's motion as it flew over mountains, basins and plains, scientists mapped how masses distributed inside Mercury. Those wobbles, combined with measurements of the planet's gentle tides under solar pull, tightened the picture of a vast, partially liquid core wrapped in a thin mantle. The numbers point to a solid inner core nested within a liquid outer core, likely alloyed with sulfur to keep it molten, and perhaps capped by a dense layer of iron sulfide against the base of the mantle. It is a small planet with a grand metallic ocean at its centre, an arrangement that explains much of what the cameras saw above. Long scarps where the crust shortened as the interior cooled, and broad volcanic plains from an era when heat could still lift melt to the surface. Then there were the poles, places of permanent night on a planet of long, patient days. Decades earlier, Earth-based radar had sent back echoes from Mercury's high latitudes that looked suspiciously like the signature of water ice. Messenger carried two tools to test that whisper. The laser altimeter traced the exact shape of polar craters and confirmed which floors were forever dark. The neutron spectrometer, sensitive to hydrogen, swept those regions and found the telltale decrease in high-energy neutrons that hydrogen produces when cosmic rays strike the soil. The verdict was delightfully paradoxical. In the cold traps of Mercury's polar shadows lie deposits rich in water ice, in some places bright and clean at the surface, in others buried beneath a thin, darker, insulating cap. The planet nearest the Sun keeps ancient frost where geometry rescues it from light. Messenger also revealed a landscape that looked freshly nibbled. Scattered across crater floors and lava plains were hollows, small shallow rimless depressions ringed by bright, high reflectance material. They cluster where volatile-bearing minerals were exposed and then lost to space under harsh sunlight and the solar wind, leaving rock honeycombed and collapsed. Hollows were not on the shopping list when the mission launched. They became one of its most charming discoveries, proof that Mercury's surface, though ancient, still hosts subtle change. The magnetic instruments returned a different kind of surprise, structure in the invisible. Mariner 10 had found a weak global magnetic field. Messenger mapped it in detail and found the dipole was not centered, it was shifted northward by a noticeable fraction of the planet's radius. That lopsidedness meant the dynamo in the core was not a symmetric, simple engine. Heat likely leaves the core unevenly, or a stably stratified layer above the dynamo muffles southern flux more than northern flux. Meanwhile, the little magnetosphere crackled with activity. On the day side, magnetic reconnection snapped field lines and opened portals for solar wind particles to rush in. At the poles, those particles smacked the surface and lofted atoms into the exosphere. Night side, the magnetotail stretched and then pinched off in miniature substorms. It was space weather performed in chamber music rather than full orchestra. but the composition was the same. As Messenger orbited, it watched the exosphere breathe. Sodium and potassium brightened and faded with season-like cycles tied to Mercury's position in its eccentric orbit, to the timing of micrometeoroid streams, and to the long dawns when sunlight first strikes cold, night-soaked ground. Images taken in sodium's yellow wavelengths showed the faint fan of a comet-like tail streaming anti-sunward, atoms pushed by radiation pressure, remade each day from surface materials and blown gently downwind. Mercury's air, such as it is, turned out to be a verb, atoms being knocked free, heated free, sputtered free, and then hopping or escaping one by one. The mission's timeline of tectonics refined an older impression into a clear history. Lobate scarps, those sweeping thrust fault cliffs, appeared far more widespread than anyone had guessed from flyby glimpses. They cut young plains as well as old highlands, telling a story not of a single ancient squeeze, but of long-lived, planet-wide contraction. By measuring how far surfaces were offset and how the scarps draped over different terrains, Messenger helped estimate Mercury's total shrinkage since its crust solidified. Enough kilometers of radius lost to crumple a rigid shell into a world of folds. The cliffs are a map of cooling written across the skin. All of these threads wove into a coherent picture of crust composition. The surface is iron-poor, magnesium-rich in many planes, and marked by elevated sulfur. Some regions show low reflectance material that likely contains carbon, perhaps from primordial graphite that once floated on a magma ocean and later was dragged downward or re-exposed by impacts. In false colour mosaics, these units trace a complex early differentiation, not a monotonous basaltic world, but one with chemically distinct provinces, volcanic resurfacing, and ancient materials that still peek through. Perhaps the most satisfying part of Messenger's work was how disparate clues agreed. The gravity field's moment of inertia said enormous core. The magnetic field said still liquid in part. The scarp said cooling and contracting for a very long time. The chemistry said formed under reducing conditions and kept surprising amounts of volatiles. The polar instrument said ice in eternal shadow. Each instrument sang its line, and together they made a melody that feels inevitable in retrospect. A small planet with a big metallic heart, a thin rocky rind, a history of early volcanism and late tightening, a whispering exosphere and pockets of frost saved by perfect geometry. By the time Messenger, out of fuel, gently descended to end its service against the surface it had studied, Mercury was no longer the shy spark that slipped away in the glare. It had become a place you could imagine walking, the levelled sheen of an ancient lava plain under a black noon sky, the clean drop of a scarp whose shadow stretches like ink, the cinnamon dust around an old explosive vent, the glitter that would lie unseen to human eyes in a polar pit where ice rests under darkness older than cities. A world once obscure stood detailed and dignified, its contradictions resolved into character. And there was a softer gift in the data too. The smallest planet taught, gently, that simplicity is often camouflage. A grey disk hid a chemical puzzle, a faint field hid a living core, a proximity to the sun hid quiet ice. By mapping everything and measuring patiently, Messenger turned maybe into hear, perhaps into look. In doing so, it revealed not just Mercury, but a method. Take your time, change the lighting, listen across many senses, and a silent world will tell you more than you expected, enough to fill the long, easy minutes before sleep with the calm astonishment that science does best. Bepi Colombo is the kind of journey that makes you appreciate patience. Launched in 2018 as a partnership between the European Space Agency and the Japan Aerospace Exploration Agency, it is not one spacecraft but a carefully stacked trio. a transfer stage with gentle ion engines and 2 scientific orbiters tucked together for the cruise. The transfer stage provides the long push. The pair of orbiters, Europe's Mercury Planetary Orbiter, and Japan's magnetospheric explorer MIO, will separate at Mercury and take up complementary paths around the planet. Getting down to Mercury is harder than it sounds. Near the Sun, gravity is strong, and without a thick atmosphere for braking, you can't just fall inward and throw out a parachute. Bepi Colombo uses a rhythm of solar electric thrust and planetary slingshots. 1 flyby of Earth, 2 of Venus, and 6 of Mercury. 9 gravity assists in all, bleeding speed little by little, until Mercury can finally catch it. The technique was mapped out years in advance, and each pass has been a precise silent handshake. Earth in 2020, Venus in 2020 and 2021, then Mercury encounters through 2025, setting the craft on course for orbital insertion planned for late 2026. Those flybys have already paid dividends. On each close pass, cameras peeked over new horizons and radios measured how the spacecraft's path bent, refining the gravity field. During the 6th flyby, Bepi Colombo skimmed the north, returning crisp views of polar craters and volcanic plains and the rim of that giant basin, more than 1,500 kilometers wide. A preview of the kind of coverage the orbiters will deliver when they arrive. It was the last of the flybys, a final rehearsal before the main performance. The cruise configuration is an elegant stack. At the front sits the Mercury Transfer Module, all solar arrays and ion thrusters, sipping xenon and turning sunlight into a steady, frugal push. Behind it rides the European Orbiter, wrapped together with a sun-shielded cradle that protects Japan's MIO from the punishing heat. This convoy is built to survive years of hot daylight, long eclipses, and the complicated geometry of inward spirals. When the time comes, the transfer stage will be discarded, the protective sun shield will separate, and the 2 science craft will take their own orbits. MIO, in a wide high path through Mercury's magnetic environment, and PO in a tighter lower loop to map the surface and interior. What do scientists hope to hear when the instruments begin their long listening? First, a clearer voice from Mercury's magnetic engine. Mariner 10 discovered a global field. Messenger showed it was oddly shifted north and connected that field to a lively miniature magnetosphere reshaped constantly by the solar wind. MIO is tuned for that space weather theatre. It will sample the charged particles and fields above the poles, measure how energy from the sun dives down Mercury's magnetic cusps to knock atoms off the surface, and watch the magnetotail stretch and snap like a glowing thread. The aim is to understand how a small, weak dynamo breathes under such intense solar pressure, and how that breathing sculpts both the exosphere and the surface. The Mercury Planetary Orbiter, lower and slower, will do the cartographers' and geochemists' work. It will refine the global topographic map with laser ranging, stitch, colour mosaics that separate rock types by chemistry, and red elemental abundances with X-ray and gamma-ray eyes. After Messenger's discovery that Mercury's crust is poor in iron yet rich in sulfur, a clue that the planet formed in a reducing environment, MPO's instruments are set to measure regional variations in far greater detail. Are the smooth plains inside basins everywhere made of similar lavas, or are there families with distinct recipes? Do those unusually dark patches represent carbon-rich remnants from ancient flotation crusts, and if so, how common are they? Answers here trace back to the earliest kitchen of the solar system, the chemical pantry near the young sun. Another target is the subtle architecture of the interior. By tracking the spacecraft's motion with exquisite radio measurements, researchers can weigh basins and mountains and reconstruct how mass is arranged from crust to core. Combine that with tides raised by the sun, tiny but measurable, and the picture of Mercury's heart sharpens. How big the inner solid core is, how deep the liquid layer runs, whether a dense blanket of iron sulfide sits at the core mantle boundary, and how heat leaks upward. Those details feed back into the magnetic story. A dynamo depends on motion in liquid metal, and motion depends on how the core cools and how light elements are stirred in. Bepi Colombo is also poised to comb the exosphere, that near vacuum haze of solitary atoms, for daily and seasonal rhythms. Sodium and potassium brighten when fresh sunlight hits night-chilled ground. Meteoroid streams trigger brief exospheric showers. Radiation pressure pushes sodium into a faint, comet-like tail. With coordinated measurements from MEO above and MPO below, scientists can tie surface sources to exospheric clouds and tails to magnetic funnels, turning what used to be a set of separate hints into a single connected system. Then there are the poles. Earth-based radar and messengers instruments made a paradox feel ordinary. In certain deep polar craters, sunlight never arrives, and water ice can persist for geological spans. MPO will map these cold traps at finer scales and in different wavelengths, probing whether bright, clean ice sits at the surface or hides beneath insulating mantles of darker material. MEO's measurements of the high-latitude magnetic environment will help explain how charged particles and micrometeoroid dust weather those frosts. Put together, the data should tell a quiet migration tale. How water arrives. By comets. By asteroids. By slow release from rock. And how it shuffles grain by grain to the coldest shelves. Geology will not be left behind. Messenger revealed lobate scarps, long, curving cliffs, almost everywhere, evidence that the planet has been shrinking as its core cools. MPO's sharper maps can time the last twitches of that global contraction by seeing where scarps cut very young planes and by measuring offsets more precisely. If contraction continued later than we think, it would tighten the link between a cooling core and a living dynamo. If it ended early, it would push models toward different inner architectures. Either way, the cliffs become more than scenery. They become timekeepers. Bepi Colombo's schedule has had to flex. Deep space missions always do. Early mission plans pointed to orbit insertion in December 2025. Subsequent updates, including post-flyby assessments, set the arrival for late 2026. The big picture hasn't changed. The transfer stage will complete its long pull, the stack will separate, and the two orbiters will begin at least a year of science. Likely more if the hardware and sunlight are kind. The best dates come from the teams doing the flying. Their latest public plans point to an arrival around November 2026. Followed by routine science operations once the orbits are trimmed and instruments commissioned. If there is a theme to what scientists hope to learn, it is connection. How does a small, metal-heavy planet hold onto liquid at its core and keep a magnetic field going? How does that field funnel energy into the surface and lift atoms into space? How do those atoms paint a tail tens of millions of kilometers long, and where did they return to ground? How did the crust acquire its strange chemistry, and how did volcanism pave so many lowlands early, and then subside into silence? Bepi Colombo's twin perspectives, high and wide for MEO, low and close for MPO, are designed like two eyes, depth from comparison, clarity from overlap. There is something quietly moving about this mission's style. It has flown past our own world, visited cloud-veiled Venus twice, threaded 6 careful paths by Mercury, and now coasts toward a rendezvous that will unfold while most of us are making breakfast and catching buses. When it arrives, the smallest planet will no longer be the dim rumour in the glow of twilight. It will be a place with clockwork weather in its exosphere, with cliffs that are slow-motion tectonics, with frost in eternal shade, and with a magnetic song still playing from a deep metallic heart. Bepi Colombo will not shout its discoveries. It will accumulate them, orbit by orbit, until the picture of Mercury feels inevitable. The kind of inevitability that only comes when you have taken your time and listened closely. Mercury is a quiet tutor with 3 very different students: the Moon, Earth, and Venus. At first glance, it looks most like the Moon, a grey cratered world whose surface has been written by impacts rather than rivers, winds, and glaciers. Both lack thick atmospheres and both preserve scars across billions of years. Yet the likeness is skin deep. The Moon is a rocky shell wrapped around a modest core. Mercury is mostly metal with a thin, rocky rind. The Moon's gravity is gentle, Mercury's is stronger, tugging craters into slightly different proportions and favouring peak ring basins at sizes where lunar craters still host single central peaks. The Moon's lobate scarps exist, but they are fewer and smaller. Mercury's are grand, sweeping across continents' worth of ground because the whole planet has shrunken more as its oversized core cooled. Even the smooth plains tell different tales. Luna Maria are basalt seas erupted from a mantle that could still well up in local episodes. Mercury's smooth plains include vast flood lavas, yes, but their chemistry, iron-poor, sulfur-rich, points to a more reducing interior, a recipe closer to a metalworker's shop than a terrestrial basalt kitchen. Earth is another contrast entirely. Our world is wrapped in air and ocean, veiled by clouds, carved by rain, and rearranged by plate tectonics. On Earth, impacts fade. Mountains rise where plates collide. Basins fill. Sea floor is born and swallowed. On Mercury, memory is the default. It keeps the pages. Earth's magnetic field is strong, with a dynamo fed by a churning iron core and aided by plate tectonics that help cool the deep interior. Mercury's field is faint but persistent. A soft hum from a small sulfur-alloyed core that has refused to freeze entirely. Earth moves heat through a thick convecting mantle. Mercury's mantle is thin, so heat leaks out with fewer detours, and the crust records the result as global compression rather than as drifting continents. If Earth is a symphony with many instruments playing at once, Mercury is a minimalist piece for metal and stone, a melody of impacts, a harmony of early volcanism, a long diminuendo of cooling and contraction. Venus is a lesson in how similar starting conditions can diverge wildly. In size, Venus is Earth's twin. In behaviour, it is alien. A slow backward spinner, cloaked in a crushing atmosphere, with a greenhouse that turns its surface into a global kiln. Where Venus hides its land under cloud, Mercury lays everything bare. Where Venus likely resurfaces episodically, bearing its older terrains under sweeping volcanic renewals, Mercury stayed geologically sparse after its early floods so that even ancient chapters are still legible. Venus has no global magnetic field despite its size. Mercury does despite being small. Those two facts alone make a useful doublet for dynamo theory. Size is not destiny. Composition, cooling pathways, and boundary conditions matter. Beneath the planetary comparisons runs Mercury's most famous cameo in physics, the riddle of its orbit. 19th century astronomers could account for almost all the slow swivel of Mercury's elliptical path, the precession of perihelion, by adding up the gravitational nudges from the other planets and the Sun's slight bulge. Almost all, but not all. A stubborn extra 43 arc-seconds per century remained. The gap mocked tidy Newtonian tables. Some proposed an unseen inner planet, Vulcan, to supply the missing tug. But the sky never delivered a reliable Vulcan, and in 1915 Einstein's general relativity made the problem vanish without inventing new bodies. Near the Sun, space-time is curved enough that the path a planet follows deviates slightly from Newton's straight expectations. When you compute Mercury's motion in that curved geometry, the missing 43 arc-seconds fall out as a matter of course. the smallest planet closest to the Sun, became an exquisite test of a huge idea. It has been confirming that idea quietly ever since. Mercury's legacy in planetary evolution begins with its surprising anatomy. A core that swallows most of the planet by radius and mass, capped by a thin mantle and crust. How does such a body arise? The answers are still refined, but the menu is clearer than it used to be. One family of explanations leans on the early solar nebula. Very near the Sun, temperatures and radiation may have favoured metals over silicates, so that bodies forming there accreted proportionally more iron. Another leans on dynamics. A proto-Mercury might have suffered one or more hit-and-run collisions that stripped away rocky mantle preferentially, leaving a compact metal-rich survivor. Reality may be a blend, a metal-friendly birthplace edited by violent encounters, followed by the Sun's young winds whisking away debris that otherwise would have fallen back. Whatever the exact mix, the outcome is a planet that tells us the inner solar system did not dispense ingredients uniformly. Distance from the Sun mattered, chemistry mattered, timing mattered. The planet's surface chemistry pushes the story further. Messenger's measurements revealed a crust surprisingly rich in sulfur and other volatiles for a world roasted so near the Sun. That single finding forced origin models to keep Mercury's lighter elements in play rather than assuming they were entirely baked off. It hinted at an interior formed under reducing conditions where oxygen was scarce enough that iron bonded with sulfur and carbon could persist to darken certain units as low reflectance material. The hollows, those small bright-edged depressions where volatile-bearing minerals, sublimed away under harsh light, turn chemistry into sculpture, showing that Mercury's rocks still whisper their composition even now. Mercury also refines our sense of planetary adolescence. We used to imagine small rocky worlds as quickly cooling to silence after an early bombardment. Mercury corrects the timeline. Its smooth plains record extensive volcanism after the Great Basins formed, and its lobate scarps show that planet-wide contraction continued long afterward, offsetting even relatively young plains. The magnetic data say a liquid outer core remains. Put together, the picture is not of a world that sprinted into senescence, but of one that glided, active early then quieter, yet still humming faintly within. For models of rocky exoplanets close to their stars, that matters. Small and close does not always equal dead. In comparative planetology, Mercury is a benchmark for extremes. It has the shortest year and one of the longest solar days. It offers the starkest thermal contrasts because it lacks air. Oven on one face, cryogenic shade a few steps away. It carries a global field despite its size. It keeps ice in polar pits while its equator smoulders. Each most is useful because it strains our theories. The 3-to-2 spin-orbit resonance shows how tides on eccentric orbits carve out unexpected equilibria. The exosphere's sodium tail demonstrates how a surface can feed a ghostly, collisionless atmosphere, one atom at a time, and how radiation pressure sculpts it. The polar cold traps show how geometry alone can do the work of climate where there is no climate, corralling water molecule by molecule into darkness that outlasts continents. Where does that leave the solar system's beginnings? With a more textured tail than the simple gradient from rock to gas. Mercury's composition says the inner disk was chemically diverse and dynamically rowdy. Its metal-rich body says that collisions near the Sun were not only common, but selective in what they removed. Its persistent dynamo says that even small cores can stay liquid, if alloyed and cooled just so. Its surface says that violent bombardment can open pathways for calm lava, that cooling can wrinkle a world into cliffs as tall as skyscrapers, and that sunlight can etch rock by chemistry without any help from wind or rain. All of that adds constraints to the early timeline, when planetesimals formed, how fast they heated, how long magma oceans lasted, how often bodies glanced rather than merged. There's a gentler legacy too in how we study worlds. Mercury reminds us that illumination angle is a scientific instrument. Low sun to see relief, high sun to read composition. It reminds us to look in the corners, the poles where light never goes, the dawn line where exospheres wake. It reminds us that first impressions mislead. A grey disk became a laboratory for relativity. A dead planet turned out to have a living core. The nearest world to the sun turned out to keep ancient frost. The method is humility with persistence. Return more than once, measure more than one way, and let the small surprises accumulate until the picture changes. If the moon teaches endurance and Earth teaches complexity and Venus teaches caution, Mercury teaches clarity. Without air or water to blur its lines, causes and effects sit close together, impact and basin and lava, cooling and scarp, sulphur and hollow, sunlight and ice. It is not that the planet is simple, it is that it is honest. And from that honesty comes a legacy out of proportion to its size. We learned that gravity bends paths in a measurable way because Mercury was there to be measured. We learned that the ingredients of worlds differ by distance and history because Mercury wears its alloy on its sleeve. We learned that silence is not emptiness because a quiet exosphere still flows, a faint field still hums, and light alone can draw a weather all its own across a landscape of stone. Stand in imagination on the lava plain under a black noon sky. The sun is large, the shadows are sharp and the air is absent. Around you are the results of collisions you did not witness, eruptions you did not hear, and a cooling you cannot feel, yet everything is visible, legible and calm. This is Mercury's gift, to show without fuss how worlds become themselves. In doing so, it tells us something comforting about our system's beginnings. The solar system did not emerge fully organized. It argued, collided, sorted, and cooled into meaning. A small silent planet kept the minutes. If you listen closely to Mercury, what you hear first is the absence of sound. No wind to comb the ridges, no waves to worry the shore, no leaves to speak softly to the dark. Only light moves here, it creeps, hesitates, and carries the day like a careful bowl. In that quiet, the planet's character becomes clear. Mercury is a world of strong contrasts and simple truths, a place where sunlight draws hard lines and shadow keeps its covenants for centuries. It is small, but it does not fidget. It is close to the sun, but it does not boast. It keeps steady time in an orbit that loops and precesses, quick in the year, unhurried in the day, faithful to a 3-2 rhythm set long ago. We have walked with it in thought. We have stood at the edge of the Caloris Basin and traced ring upon ring, the echo of a single instant that travelled around the globe and left a field of broken hills on the far side. We have wandered the smooth volcanic plains and the older, pitted intercrater ground, reading age in crispness and chemistry in colour. We have climbed the lobate scarps and felt the planet tuck itself inward by degrees, the crust stepping over itself to fit a shrinking interior. We have peered into shallow, bright-rimmed hollows, small places where a sun too near draws secrets out of stone. We have looked toward the poles and imagined the older-than-history frost hiding in the everlasting night of deep craters, and then turned our eyes to the horizon to watch a sunrise so patient that it teaches the word itself anew. We have also listened beneath the surface where Mercury carries an ocean of liquid metal around a solid heart. That quiet ocean conducts a slow music that writes a magnetic field into space, weak compared with Earth's, yet exact and enduring, offset and distinctive, proof that motion persists below even as the crust wrinkles above. It is a reminder that small is not the same as simple, and near is not the same as empty. The smallest planet can hold a dynamo. The planet closest to the sun can keep ice. A world without weather can still be busy in ways our senses must learn how to see. Mercury has always had a way of drawing out good questions. Why does it run 3 spins for 2 orbits? And what does that make of noon and night? How does a planet that should have cooled into silence keep a field alive? What kind of kitchen in the early solar system could bake a body so metal-rich and yet preserve sulfur and other volatiles? How does ice find shadow in a place where light is so confident? Matching answers grew from patient instruments and a habit of returning. Mariner 10 taught us to expect surprises and to value a clever path. Messenger taught us to map slowly and measure many ways, until chemistry, gravity and magnetism agreed on the same story. Another traveller is on the way, and it will add new lines to the melody already playing. Yet the essential theme has emerged. Mercury is not a footnote in other planets' stories. It is its own text, short but dense, the kind of book you keep on the table because it reads differently every time the light changes. There is a way in which Mercury makes everything feel more legible. On Earth, with air and water and life, causes and effects are layered and braided. The world is exuberant with processes that speak over each other. On Mercury, much of that chatter is absent. Impact makes basin. Basin invites lava. Lava cools and the planet tightens. Sunlight etches, shadow preserves. The sequence is not cold, it is clear. That clarity turns out to be a gift, because it lets us test ideas about how rocky worlds begin. Cool and AE without the complicating chorus. When we then look back to our own planet or across to Venus, we carry a better sense of which lines belong to deep interior rhythms and which are ornaments played by air and ocean. To spend time with Mercury is also to change one's scale of patience. Our days are full of immediate things, messages, clocks, the quick turn of weather. Mercury asks you to imagine a dawn drawn out over weeks, a noon that pauses, a sunset that lingers until you can feel the planet motion in your bones. It invites you to think of heat and cold not as comfort or discomfort, but as principles, to see that a shift of a few steps can trade one for the other, and to remember that geometry is a quieter climate than atmosphere, but no less exact. It rewards the kind of looking that takes time, low sun, long shadow, repeated passes in different light, the kind of attention that suits a bedtime mind, where detail slows and settles and finds the right place to rest. And yet, for all its seriousness, Mercury makes room for gentle humour. A planet famous for speed manages one of the longest solar days. A world next to the sun keeps ice. A body thought too small for an active heart hums with a field. An airless world wears a comet-like tail of sodium atoms, as if to remind us that air can be a verb as well as a noun. These are not punchlines, they are smiles, small instructive reversals that leave you a little lighter for having learned them. There is another feeling that grows while tracing Mercury's path. Gratitude for the craft of inquiry. Engineers shape trajectories that borrow from gravity, like a careful dancer borrows weight from a partner. Instruments measure in colours our eyes cannot see, and in times too brief for any hand to count. Teams work for years to assemble a single mosaic, a single curve on a plot, a single pass in darkness that catches the edge of a crater and proves it is shadow forever. The planet is silent, but the attention brought to it is full of human sound, calculation, argument, patience, and the soft celebration that accompanies a line of data that finally makes a mystery less so. To notice a small world honestly is to practice a kind of kindness. If there is a message to carry into sleep, perhaps it is this. Even the smallest world has room for a great story, and most of that greatness is made of small, exact things. An angle of light, a fraction in a resonance, a handful of atoms leaving a surface, a cliff that drops by a clean measure where rock slid upon rock. Put together, they become character. Mercury is the messenger here, not because it runs fast, but because it shows how much can be said without raising a voice. So let your breath slow with the planet's long dawn. Picture a lava plain under a black noon sky, a crisp horizon, the sun a little larger and a little whiter than you expect. Imagine the shadow at your feet as a ribbon of cold, and a scarp in the distance drawing a dark straight line across pale ground. Think of the deep interior, a liquid metal ocean turning so slowly that it makes magnetism out of time. Think of a crater floor near the pole, quiet enough to keep frost for ages, and of a sodium tail streaming invisibly downwind, renewed each day by sunlight alone. Consider how a small world can keep good records and how, by reading them, we learn to listen better elsewhere. When you next see a tiny spark near the horizon, early or late, you will know a little more of what it is. Not a mere point of light slipping away into glare, but a patient planet that has kept minutes for the solar system since before there were names for minutes to keep. It is content to circle, to turn, to mark long dawns and longer dusks, to let physics write poetry on stone. And as you close your eyes, that is the note to end on, a quiet confidence that the universe is full of stories precisely where it seems most bare. Mercury wears one such story openly. All you have to do is look, wait a little, and let the silence do its work.